Today we are at the University of Nottingham in a conference that has been organized by Leo Parry, Cameron Bunney, and Cisco Gooding. So I'm going to give it right away to Cameron, and he's going to do the introduction to this conference. Thank you so much for organizing it.
Thank you for the opportunity to host this event. And I wanted to thank everyone virtually and in person who's coming, and all the speakers who have prepared talks for us today. This conference is really split into two halves. First, we'll have the more theory section, and then we have the experimental section. So at this RQI hub, we have a variety of people interested in both experimental aspects of physics and the theoretical underpinnings of those experiments. So we're going to hear a lot about things to do with the Umra effect, analog gravity, and also techniques for measuring, so things about holography. So without further ado, I'd like to welcome our first speaker, Jorma Louko, to give us an overview of the theoretical work here. Where would you like it?
Where does it work? 5, 6. 5, 6, am I on? Okay, thank you very much for the organizers for putting together this Nottingham node of the international series of meetings. And thanks for inviting me to open with some introductory remarks, as I understand them, to the type of theory research on relativistic quantum information and related topics that we do here at the University of Nottingham. So I should come clean and say that my background is solidly in theory, curved space-time quantum fields, to some extent quantum gravity. And that is what I will be mostly addressing here. But over the past 10, 15 years, I have become convinced that this is an area that has solid experimental connections. This is a topic that can be pursued in collaboration with experimentalists, and that collaboration between theory and experiment is very much the overall tone of all of today's talks. Plan. So I'd first like to tell a little bit about the relativistic quantum and information research that we do here at the University of Nottingham. And then I'll tell at a general level about the Unruh effect, the effect that is a paradigm of the things that we'd like to analyze, what we'd like to measure, and related phenomena, and where we are from the 70s, totally theory, to the present, where we have an interplay of theory and experiment. Let's start with a question. I understand that the local crowd is a Nottingham crowd, okay? And the real-time interaction with the international audience doesn't quite work. So in some sense, this is a thought experiment version of a quiz. But suppose you were asked, name a famous person from Nottingham. Right, I have a pretty good guess as to what the first name is that comes to your mind, but I'm not heading that direction here. So I should like to think of a person that is demonstrably a non-fictional person. And in case you think of the Sheriff of Nottingham next, no, I don't want to go that direction either. I want to think of a Nottingham person with a clear mathematical physics connection. In fact, so clear a connection that all of you, whether in this room or everywhere listening, have probably used the work of this person. Maybe studied it, maybe have taught it.
You.
Well, I'm thinking of a different order of magnitude, both in time and space, and in space-time, right? So we can't really do this interactively. So I'll put up a picture first. So we are talking about early 1800s. We are talking about a Nottingham miller called George Green. There is his windmill. It still stands. It's been restored. It's a working windmill. You can go there, you can visit, you can go up there, you can, in the shop, you can buy flour that has been ground there in George Green's windmill. Okay? And the name, it's a fairly common name, so as such, it might not ring a bell, but the mathematical physics connection is, this is the Green of Green's functions that we know, love, and use. Okay? Green was a miller by professional. As a mathematician, he started entirely self-taught. He had about 1 year of formal schooling. And then, when the wind wasn't blowing, he taught himself mathematics, continental mathematics, which was a novelty at that time in UK. And he wrote an essay, right, mathematical analysis to the tutorial, to the theories of electricity and magnetism. This is where he came up with the idea of Green's functions. He also came up with the idea of potential, as in electric potential and so on, in this essay. He published it by crowdfunding. He went to his friends and he said, okay, if you promise to pay me this much, you can get a printed copy of this essay that I'm writing here. Okay, and he got published. And this is where Green's functions came from. Later, he got some formal education in mathematics. He went to Cambridge, did a degree there, became a college fellow, wrote half a dozen papers. One of those papers is actually quite relevant for today. One of his papers is about water waves in a canal. That's closely related to the kind of research that we do here in Nottingham. And in that water wave papers, Green introduces something that we would nowadays recognize as a precursor of the WKB or JWKB approximation in quantum mechanics. So we have solid traditions in mathematical physics of the kind that we are doing in Nottingham, going back to some 200 years. The University of Nottingham cannot take credit for Green. The university started some decades after Green had passed away. But the university is here. It is a major research university. And so we do relativity quantum information. We do relativistic quantum information. And as things often are at British universities, these topics are split between physics and mathematics. Some of it is done in mathematics, some of it is done in physics. So, and I've illustrated the split over here. So we've got a School of Mathematical Sciences where we have, first of all, we have the gravity laboratory, Silke Weinfurtner's gravity laboratory, that is at this forefront of the interface of theory and experiments on analog space-time. Then we have a gravity group. We have a quantum information group. It's quite a lively group. They tend to do mainly things that are not particularly relativistic, but there is lively interaction going on there. There's also some quantum gravity type quantum mathematics, and there are interactions over there. So that's on the mathematics side. And then in the School of Physics and Astronomy, there's basically theory and experiment of solid state of various kinds and known by keywords put over there. And then there's a particle cosmology group. And so we are quite a lively bunch with lots of connections. Right, and it looks like we might be split. Not really. I mean, we have organized ourselves into the gravity-oriented things. We have organized ourselves into the Nottingham Center of Gravity. Okay, I did not come up with that title, but that's what we are called, Nottingham Center of Gravity. And right, so it includes people from all of this, and so that's the overarching way how we are organized. And I could not resist putting up here a photo. So this is at the Nottingham Center of Gravity web pages. So the big part, it's a genuine photo from about now, some contemporary photo. It's the main administrative building of the University of Nottingham main campus here. And in the inset, you have a photo from 1930 taken at the very same location, and that is from a visit of Einstein to the University of Nottingham. In fact, we still have the blackboard that Einstein used for his talk. It's preserved. It's in one of our meeting rooms. If you Google up the Einstein blackboard, there are exactly two hits that come up. One is at Oxford, in Oxford at the Museum of Science there, and the other one is here at Nottingham. We think ours is the better one, okay. So we do research relevant for the topics of this series of meetings. What I'd like to do next is, I'd like to look at the motivating theory behind the type of research that we do. So the general theme is really modeling quantum fields, relativistic quantum fields in the laboratory and the theory supporting it. But if I were to start from a key concept that underlies our thinking, the key concept would be the Unruh effect. Okay, so this is a prediction from the 1970s. Prediction in relativistic quantum field theory that says if you take the Minkowski vacuum, the no particle state, the traditional no particle state in Minkowski space, and then you, as an observer, you accelerate through it uniformly, linearly with constant acceleration, then that vacuum doesn't look like a no particle state to you anymore. Instead, it looks like a thermal state. You react to that state as if it was a thermal state in a temperature that is proportional to the seat of Pan's acceleration that you feel. There's the acceleration and there's the numerical constant. So this is a prediction. It's a prediction from the 70s. Was a surprise when it came, okay? But the input, it's entirely standard quantum field theory. There's nothing exotic in the input. There are some approximations, like you need to wait for a certain amount of time and the coupling needs to be sufficiently weak and so on. But this is an entirely standard prediction of standard quantum field theory. And this isn't just some equations that you put on a piece of paper. This is a prediction on which you can imagine a Gedanken experiment, a Gedanken test. So my favorite way to think of it is in terms of excitation and de-excitation probabilities of some system you have. So suppose I am in my spaceship, accelerating linearly. I can feel like I'm using my rocket engines, and on the shelf of the spaceship I have jars of different types of atoms, like this: antimony, arsenic, aluminum, selenium, and so on. And once in a while I look in each of those jars and I check what fraction of those atoms is in their ground state, what fraction are in their excited state. And I see that it's different from jar to jar. And in particular, I'll see that it's different from what I'd have if I wasn't accelerating at all. This is what the Unruh effect predicts. It says, well, that the downward probability transition and the upward probability transition, they are related by the exponential law. We know it as the detailed balance law, where the gap, the transition gap between the ground state and the excited state is over there, and there is the temperature now being proportional to the acceleration. So this is something that you, in your spaceship, accelerating, you could go and imagine testing it. Well, so you could say it's so real an effect that you can cook your steak with it, given sufficient acceleration. However, to date, no steaks have been cooked with this phenomenon. And the thing has, why? It has to do with the numbers over here. You see that the dimensions here, they don't quite match. There are some constants of nature missing. If I put the constants of nature in, right, No stakes good because there's a small number in everyday units upstairs, there's a large number speed of light in vacuum downstairs, and so to get to 1 Kelvin you'd need to tend to 20 meters per second squared. So there's no direct experimental test of this prediction. It's a standard kind of prediction, but there's no observation. So that's the showcase example. There is a larger context here. I mean, this is standard Minkowski quantum field theory. The history didn't come from thinking of Minkowski quantum field theory. The history came from thinking of what's happening in curved space-time, okay? And that's very much the formalism by which this prediction is found. And so the bigger context is you have a local quantum system, like your jar of antimony atoms or something, interacting with a quantum field. And usually here you are interested in a quantum field that's spread all over space-time. It's not like a typical quantum optics scenario where you say you have a focused laser here and you're interested in what the laser does. You are here interested in a quantum field in a state that's spread all over, like the vacuum, could be a thermal state, could be something else, but a very non-localized state. And that's the bigger context of here. So what happens in this sort of interactions with a local quantum system and a field that's spread all over? If we go really historical, I mean, that there is such an interaction. It's been known for, I don't know, since 40s and so on. I mean, if you think how the fluorescent tubes in this room works, there's light that comes from here. You excite the atoms there by electricity, and then there's a spontaneous decay to a lower energy state. How does that spontaneous decay come about? It comes by interaction with the vacuum of the quantum electromagnetic field. This is not something you can tell a second-year undergraduate student, right? But it's quantum field that causes the downward transitions over there. Here we are thinking of this phenomena in the larger setting of non-trivial motion, possibly some non-trivial spread out states. And we could think of time-dependent situations. One of my favorite examples is a local observer falling into a black hole that Hawking radiates. What does that local observer see when they are still far from the hole, when they get closer to the hole? Maybe when they get in the hole and have crossed the horizon. And I am reminded that in last week's session, Rob Mann talked about research in that specific problem. So this is the larger context. I'm going to be qualitative here, and so these are the only equations that I'm going to show. But I'd like to next list what kind of problems this setting creates, what kind of problems you need to start thinking about. And still on the theory side, so facets of theory, if you like. So first there's this notion of a local quantum system. What do you mean by this local? I mean, so you might think like there's an atom, okay, and it's localized in certain sense, but atoms are complicated things. There's, I don't know, spin-orbit coupling, and they are different types of orbitals. They are messy things. So how would you sort of model a local quantum system? Your first thought might be, let's go point-like. Get away all with those finite size complications and so on. Now, this might give you pause, because when you start studying quantum field theory, one of the early things you learn is that if you ask things about a space-time point, you can expect that things are going to turn singular. So you might feel uncomfortable about this. Now, if you say spatially point-like, so you still have a time dimension in which you go through the space-time. There you have some more hope. Okay? But it's a non-trivial question. Does this make sense? It works more often than one might expect. I mean, so this goes back to DeWitt's observation in the 70s. So you often work in perturbation theory, and often if you work in low-order perturbation theory, the point-like system, it works way better than you might think. And in low space-time dimensions, it works particularly well. But ultimately, it does produce singularities for you. It tells you that you are trying to do an idealization too fast. For example, if you often if you ask about the experiences of a single atom, you're fine. But if you start asking about entanglement between two atoms moving in different places in this language, then the point-like character, it starts to create a problem for you. So that's something you need to think about. If not point-like, then what? I mean, some sort of confining potential, maybe. Maybe something like a two-state system with a spatial profile. So how does that work? Well, there's a lot of work on that topic. And so if you ask simple enough questions, it works beautifully. And there's a vast literature going on it. But I would argue, if you start asking questions that are too delicate about how things are localized in space-time, you find that these profile systems, spatial profile systems, they tend to violate relativistic causality. And this is an observation that goes back to Sorkin in the 90s and has been developed much since. So for some observations, it's fine. Ultimately, of course, you'd like to use relativistic fields. We think that the space-time, our fields that live in a relativistic space-time, they are relativistic fields. They are hard to localize. I mean, you can sort of localize the photon here, but then it keeps spreading when it goes. So they are hard to localize. You might try to localize them with a cavity, and there is literature on this. So you postulate that you've got a cavity that's totally confining, maybe even partially confining, and then you let it move in space-time. So, there's literature on that, but you need to then start thinking what is the sense of localizing one field and maybe not localize other fields. And also you need to think about what do you mean by rigid cavity. This is the rigid body problem in relativity. It doesn't really exist except in certain special cases. So these are facets of the theory you'd need to think about. I've got a second overhead about these facets of theory. Another thing you will need to worry about, how do you do the coupling between your local system and your spread out field? A lot of the literature goes perturbatively small. You do perturbation theory in a coupling constant. Okay, and that's certainly a good place to start. We love doing perturbation theory, don't we? Right? And yes, at least in theory, right? It works, right? It has some issues. In particular, if you wanted to consider the long time limit, you can see there's an intrinsic contradiction. If you want your interaction to be weak so that perturbative treatment is valid, but you want your time to be long so that there's lots of time to interact. I mean, there's a problem of internal consistency. You need to address this somehow. And I think for the purposes of today, let me leave it at that. You could talk about a simultaneous regime of large time and small coupling and so on. But there are significant technological things that you need to worry about here. You could try going non-perturbative. That's, of course, much more difficult. On the sort of mathematical side, theory side, there is some work in that direction. I've mentioned a few things here. They tend to be existence-type analytic work, and they are good. I mean, so there are sort of mathematics-type, existence-type results, and then the challenge is how would you convince an experimentalist that an existence-type result is something they should be worried about, or they should pay attention to, but it can be done. Then there's numerical work that's quite common. For example, there's an early paper by Hu and Lin where they look at the Unruh effect in a genuinely non-perturbative regime. And they find some regimes where the Unruh effect is a transient effect and goes away if you follow the system fast enough. But so this non-perturbative thing, it's another facet you need to think about. And finally, right, you need to think about this time dependence. So you might be interested in something that's stationary, but then you need to worry how do you start the interaction, how you do end this interaction. Or you might consider a genuinely time-dependent situation, like this observer falling in the black hole. That is a genuinely time-dependent situation, and then you need to worry how you characterize this genuine time dependence versus any switch on and switch off type phenomena that you've introduced when doing this. So there are some theory issues you need to consider here. Toward experiment, right. So we are talking here about the analog space-time program that says there are laboratory systems in which you have excitations obeying a relativistic wave equation. The seminal paper here was Bill Unruh's paper from 1981. That was in the water waves context. Then there's Bose-Einstein condensate, there's helium, and so on. And we know that, well, so if there's a relativistic wave equation here, same equations have same solutions as Bill has as Bill Unruh has been repeatedly advocating. So what can you test a relativistic system by these systems that have a non-relativistic fundamental physics, arguably, but an effectively relativistic field equation. And that's the really the interface that we are interested in. And the specific problem that I'll mention here is the Unruh effect, but in circular acceleration in this analog space-time context. Now, how should I think of the time budgets? Okay, thank you. So, right, so we'd like to think of the circular motion, we'd like to probe the circular, the Unruh effect in this context. Water waves, well, water waves are pretty classical. The Unruh effect is supposed to be a quantum effect. You can test some of the underlying classical dispersion things with water waves, but you wouldn't expect to test the genuine quantum regime with water waves. But we have Bose-Einstein condensates, we have helium surface waves, and in those systems we have a genuinely quantum system, and there you have an effective relativistic field equations. Those are a good arena for looking at the Unruh effect. So Bose-Einstein condensate, helium, they are good things. And why do we think this is better than the space-time setting with my spaceship and the jars on the shelf? Remember the formula, one of the two formulas that I showed. What was the formula for the Unruh temperature? It had the speed of excitation, speed of light there in the denominator. And that was one of the reasons why in the space-time setting Unruh effect is difficult to observe. But if you go to one of these systems, the effective excitations, they don't go at the speed of light in vacuum. They go at, well, they go at a speed much less. And that makes the effective Unruh temperature higher. It's something you can, it's something that's more easily experimentally accessible. So good systems. Circular motion, why? Well, if you try to do linear motion in a lab, you will eventually run out of your lab. I mean, given a lab with normal size budgets. But if you use circular acceleration, you can run your experiment in a circular motion, in theory, an arbitrary length of time. Okay, so that's a good selling point for circular motion. Another circular motion has to do with the technical aspects of how time dilation occurs in the theory of the Unruh effect. For the purposes of today, let me just say that if you are working with this circular motion, those time dilation things, they are entirely straightforward. You don't need to ask your engineer to do something with your Bose-Einstein condensate or your helium to put it there. These time dilation things, they are entirely at the end, at the data analysis. So this is a nice setting. Now circular motion, it's not linear motion. So the Unruh effect there. It's not quite the same as the detailed balance formula that I showed, but right, long story going back to the 80s and so on. But the bottom line for here is it's almost like it. There's some additional dependence on parameters, but for the purposes of detecting something, there's something to detect, and it's basically the same thing. And finally, so remember we wanted to have some material local system going around, in this case going around in circle. If you are using these Bose-Einstein condensate or helium, you can simplify things, and instead of putting a matter system there in your field, in your effective quantum field, you can collect and sample those fluctuations, those quantum fluctuations, vacuum fluctuations by a passing laser beam, and then do data analysis on them later, and we'll have talks, we'll have that discussed in later talks today. And on that note, I think I would like to end this interview. So over the past years, I have become convinced that the analog space-time paradigm, analog space-time system, it is a viable place to look for, to test experimentally predictions of relativistic quantum fields, and in particular this question of how a local matter system interacts with a spread out quantum field. And it's at that interface that we are working here. And we take PhD students, we host postdocs, sometimes we have internally funded postdocs, sometimes we host postdoc applications to research councils. Do get in touch with us. And on that note, I'd like to end here.
Thank you, Jorma, for the very comprehensive overview of everything we're doing theory-wise at the moment. I'd like to open it up to any questions, both online or from the room itself. So if anyone has any questions first from the room. Yes, Vitor.
Jorma, in your opinion, what are the challenges for us when doing the experiment to try and measure the analog Unruh effect? What do you think are the main things we should be careful about, other than the experimental technicalities?
I think we'll have a talk about data analysis later today. That is something I would dearly like to understand better. On the theory side, that I would see that as a sort of major things where things need to be cleared up.
Okay. Are there any other questions in the room? Are there any questions online? Okay, well, if not, then thank you very much again. We would like to thank you again for speaking. And I'd like to welcome our next speaker, Adam Wilkinson, who will be speaking about back reaction in the circular Unruh effect. I'm still wearing a microphone. I don't have to take it off. That was easy. The stage is yours, and here's Adam with back action in the circular motion Unruh effect.
Thank you very much. How is this? Is that too close? Is the mic going to be a problem there? If there is, then chat will let us know. Yeah, we're talking about the back action in the Unruh effect. So it's kind of a weird talk to go first, because most of the talks here will talk about the Unruh effect and how the detector changes, how the detector transitions. It's a very traditional way of looking at the Unruh detector field interaction. But instead of that, I'm going to be looking at the, I think, just as interesting counterpoint to that, to what happens to the field after it interacts with a detector. And I think there are equally interesting quantum relativistic nuggets to be found deep within that question. So I'm going to start off by just quantifying that field state. I'm going to quantify that thing that you get in the field after the interaction instead of what you get in the detector. Then I'm going to specialize down to 2+1 dimensional circular motion, a kind of motion that you'll be very familiar with by the end of today. And then I'm going to show you some plots, and that will be the good bit. So stick around for that. So to start off, let's define the things we're working with, we have a detector. We have the underwood detector, a two-level system with an initial state, which is defined here as 0, and a secondary state, E. I will try my best to not call it an excited state. If I do, I'm messing up, because it's not necessarily excited. The gap between the initial and secondary states can be positive or negative. There can be excitation and there can be de-excitation. And they're both interesting questions. And then they interact with this Hamiltonian in a very traditional way. There is plenty of literature on this, Unruh's 1976 paper being a very good example, which is where he first mentioned it. Was that the first time? I'm actually not sure of that. But we have a constant using perturbation theory, this lambda that I will try and point at with a laser that I don't point in my eyes. There we are. This lambda here is a constant we need for perturbation theory. There is also a chi, which is a switching function that I'll talk a bit more about later on, which defines how we turn the interaction on, how we turn it off. The detector monopole moment operator sits in here, which gives the detector a degree of freedom to transition up or down, however it sees fit, and be coupled to the field. And this is specifically the field along this x of tau, this proper time of the detector, along the path of the detector, parameterized by its proper time. Once we have the interaction Hamiltonian and we have our perturbation theory constant, we expand in time-dependent perturbation theory. For that, we need a Dyson series. And I'm going to go a bit further back than most things do. I'm going to try and explain how we get to this field state. So we evolve it with a time evolution operator. We set our initial conditions to be at -infinity, and we're going to evolve to some future time. And we set our upper limit here to infinity because we're looking after the interaction. Because we're after the interaction, that upper limit doesn't matter. Our Hamiltonian is 0 as long as we're after the interaction. So this upper limit can be anything we want. We can just kick it all the way up to infinity and the maths becomes possible. Difficult, possible. So from here, our initial conditions that we set, we have the initial state of the detector and a vacuum in the field. And then we act on it with the Hamiltonian. We substitute the Hamiltonian in here, and we get a little bit of a mess. Not a bad mess, a little bit of a mess. This thing here is kind of messy. This is a one-particle superposition in the field modes. And that is the thing that is emitted that we're trying to look for when the two things interact and the detector transitions. For this talk, I'm just going to call it V. I'm going to completely ignore it because explaining the details of those numerics is a pain that I will not share with you. And there are two states here which result from the two possibilities to lowest order in perturbation theory in the field state. Either nothing can happen or something can happen. Nothing can happen, or we get a transition to the secondary state, and in that transition, the field changes states to this V, this emitted other field mode, which is a bunch of one-particle states. From that, to say anything about the field, we need to find observables in the field. We need to choose an observable. We need to look at that observable. And you actually find, if you plug in, the mouse is in the way. If you plug in, find the expectation value of any field observable A, and it's just tensor product with the identity for the detector because we aren't observing that yet. Well, we get the vacuum expectation value of the observable A, and we also get this field state V. So basically, to leading order in perturbation theory, as far as we know yet, we have a vacuum contribution that we will set to 0 because it's constant everywhere, and we have this perturbed thing that we're going to actually look at and that I will try and plot and find. And for the sake of this talk, I'm going to keep it simple again because the numerics, as I think I've hinted at one too many times, are a pain. So I'm going to look at phi squared, a very simple case, the amplitude of the field. Future possibilities could expand to look at the stress energy tensor, T00, the energy density, particle number density, everything's accessible from here. It's a matter of what to choose and what is most relevant for literature, what you can find the most information from. And also what you can calculate. And with that, we need to specialize down and talk about specifically, what am I working with? I'm working with, as I said earlier, 2 + 1 dimensional circular motion. There is a detector, it goes in a circle through time, it spirals and spirals forever. I think this is a very interesting geometry and trajectory to look at for a few reasons. First of all, the circular equivalent of the Unruh effect is not something that's as well understood. It's not something which is as well behaved and as clean. There is this notion of a Bugli-Above transformation, which is how you can derive the Unruh effect in full in the linear case. That whole notion is unambiguous in the circular case, which means that directly finding anything in the traditional way is much more difficult. The other reason, and I'm not sure if I should have put this on here because this isn't something that we've actually worked out yet, but there is the potential for an analogy to experiments that are going on in Nottingham that you'll hear about later on, potentially measuring certain field observables through that, which would be also interesting because analog gravity is fun, as I hope you'll agree with me later on. Finally, the last little wrinkle that I need to talk through before we get to something more interesting and more fun, which is obviously graphs, is the switching. How are we going to define the switching? Because as I mentioned earlier, our formulas are only valid after the interaction has stopped happening. And to get to that point, we need to find some switching which switches off, and then we look at it at the point where it switches off. But to extract the most information from the interaction, to get the most excitations out of the field, you also want a very long interaction time. So what we use for these plots is what we call a half-infinite interaction, where before 0, before some time, it is, and for all time before that time, we have 1, and then we have a gradual switch off over a certain duration that we can control, ideally a fairly fast one, so we can really look at the interaction, and then it's 0 after that point, which means that we can look at the field exactly here, where the interaction is 0, and any time after that, and we can evolve through and see how the interaction evolves. Enough of the boring stuff. So we get spirals. So this is a space-like slice of the field, specifically of phi squared over the field, at a particular time. And this is specifically at the time when the interaction is 0, the first time that we can ask this question. And we get these spirals that have been plaguing me for far too long. The shape of these spirals is actually very predictable analytically. If you imagine the detector was holding a laser beam and it ran in a circle, the plot that laser beam would put, the tangent null vectors along the path of the detector would plot out this exact spiral shape here. What we've got here is, to keep explaining things, there is a velocity of 0.5 c on the detector, and the detector switches off over the course of 1 cycle. So from, I think it starts here and the detector ends there. We have 1 rotation for the switch off time of the detector. And of course these plots move, because that's much more fun. And what we see here is interesting different interactions for different energy gaps. Positive and negative energy gaps give this interesting different behavior, and around the energy gap 0, you see this much more spread out response. And I was very proud of this. I was thrilled, and I sent it to Bill Unruh to look through. And he wasn't as thrilled as I was. So I got an email that I won't bore you with right now, but the main thing is the sentence, "This answer means nothing." I wasn't thrilled about this. I haven't wasted your time, because I think there is genuine, interesting information in what I've shown you. But this was a bad day for me. So what did he mean? Well, back here, remember, if your attention span is long enough, you might remember these equations for the field state and any observable that we're trying to measure. The issue was I hadn't gone far enough. If you expand this lambda squared term in the state, and I'll explain why that you do that later on, then you get this initial state of the detector and a two-particle state in the field. And what happens is you do the same maths, you find an observable, and to leading order in any observable you try and calculate, you get this correction here, this non-zero term coming from that two-particle state. And what this corresponds to is the detector transitioning twice, is where you get this from. So you get two particles emitted, one from the detector going up, I guess, or down, one from the detector transitioning to the secondary state, and one from the detector transitioning back to its initial state. So there are two distinct things happening here, technically three, because nothing is also a thing that can happen, and what you get is a superposition of these three possibilities. And then, after modifying our equations in the way that Bill told me to, I get much more interesting graphs, I think. There's a lot happening here. So first of all, you'll notice we now have negative values on all of these graphs. Before, everything was positive, and that's something which is predicted in some of Bill's older work. He had a 1986 paper where he talked about emissions always being positive, the stress energy tensor. The stress energy tensor is always positive if you don't do this correction, which is what I saw. And that's an issue that can lead to infinite energy being extracted from the system through some mechanisms. This correction is much happier. And what you're seeing here is a negative energy contribution from that two-particle state. From that, sorry. It's not energy here explicitly, but this same thing holds for T00 as well. And you see this negative emission coming from that double emission. And that double emission is more likely for excitations. And the reason for that is that after the detector has, if the detector has transitioned to a secondary state and that state required an upwards transition, it is then unstable. It then wants to go back down again. So if you have excitations, you're much more likely to get this double transition, which is where you're much more likely to see this negative bit. The other thing that's interesting on here is this little trail here that you see only at E bar is 1.1. That trail is the energy impulse from the switching itself. The switch off happens over one rotation, as I mentioned earlier, and the field contribution that comes from that switching is evident here. It exists here, but it's much less noticeable. At this E bar is 1.1 with this negative field emission, there is a really strong upwards kick that happens just from the switching. And that is less prominent on most of the other graphs. And there's plenty here. I could talk about these for hours, but I won't bore you. But I will animate them, because that's just more fun. Yeah, Silke?
So, why is it just repeating the video, or why is it
Yes, it's repeating the video. So this is from pi to 5 pi, which is pi is where the interaction has just finished, and then 5 pi is just an arbitrary stopping point where it was.
What is surprising, perhaps to me, is basically if you had a finite size system, the waves would come back with you. You'd get, these are. So what are we looking at?
This is infinite. So this is not finite size.
But is it
This is Minkowski.
excitations you inject into your quantum field, and this how big are these excitations? Can I think?
What do you mean, how big are they? We're working in perturbation theory, so these are just perturbations that are of an...
Have an amplitude, no?
This is the field amplitude, but up to an order of perturbation theory. So we aren't. So the exact height of these is only relative to each other. It's not as relevant on its own.
So if I interact with my quantum field, the detector that interacts with the quantum field theory, if you increase, for example, the coupling between the detector and your quantum field, are these perturbations larger? What sets, I mean, you say it's up to something, but can you make it an absolute value? Can you say, like, what do you have to, we're talking about back reaction. How can you reduce back reaction? That's my question. So you have back reaction. What if I want to reduce it? What would I need to do?
It would depend on the observable you're trying to minimize. For the field amplitude here, for phi squared, you can minimize it by actually, for any of them, you can minimize it by optimizing the excitation gap of the detector, or the transition gap of the detector, between positive and negative, and large value and small values. But it would depend on the observable that you mean to which value of gap would minimize the back action. So here, this phi squared, the magnitude of it is minimized for just a large gap, means that it's less likely. T00, based on some earlier plots that I made that I have a level of confidence in, suggested that the higher the excitation gap, the less likely for T00.
So if this comes at a cost, that you also minimize the annual effect, right? If there's, you say, well, once I don't see anything in my detector, I also don't inject an excitation in my quantum field, then it just means you made the effect small. So my question would be, is there a way to maximize the annual effect? And I think the answer is no, but maximize the annual effect, what you measure on your detector, but reduce the back action.
The only other three parameters that I have here are the velocity and the duration of the switching. Both of them I can imagine having equal impact on the Unruh effect, but I can't know that for sure. There's a chance that there is an optimized switching, which kind of, where you still see Unruh effect, but you reduce the impulse of switching into the field, because, as I say, there is a emission from the switching itself. But I imagine, I mean, if you increase or change V, you'll increase or change the magnitude of this, but you'll do the same thing for the Unruh effect. So I can't think of any degree of freedom that I have that could let me do that.
I think that's a very interesting discussion to continue in the lunch break. So, Adam, if you'd like to continue.
Yeah, I'm pretty much done. Oh, I've also got them in 3D. Me and Jorma. That was an accident. I genuinely had forgotten. Me and Jorma continually argue as to which one's clearer, so I thought I'd include both just to be safe. If anyone gains any further insights from these, then please let me know at the lunch break, because I'm apparently low on time. For now, I'm just going to summarize. I'm asking what I think is the underrated but very important question of how does the field react to a detector as opposed to the other way around. There is a general procedure and there's a general derivation that I hope to use in future in a variety of situations. But for now, I just have these plots of 2+1 circular motion. If there is an excitation requirement, then you have this more of a negative field emission, which comes from this double transition. And for certain values of the energy gap, you get a larger impulse from the switching. So if you want to minimize that, you'd either need to have smoother switching, which would reduce how much you can see in the plots, or you'd need to pick energy gaps such that the switching has less of an influence. And finally, be careful when working in perturbation theory, and be doubly careful if you're emailing Bologna about it. I have some references, and I'll accept any questions now. Thank you very much.
Thank you very much for that talk. If there are any questions, I think I'd like to start it off and ask.
Yeah.
So when your detector is probing around this rotational frequency, so when this E bar is equal to omega, what happens when it's actually equal? So I know that in other aspects of the circular motion under effect, this is a really special frequency when probing. It's if looking at thermal effects or finite size effects, this is constantly appearing. So what really happens at that frequency? What do the graphs look like as you get closer to E?
Well, that plot will be closest to this one, is your question, yeah?
Yes, what happens as one gets closer and closer? Does this amplitude increase?
Not that I know of. The maximum amplitude here, I mean, this is phi squared, this is not T00. T00, I think, would have more content, but it's harder numerically to calculate. What I can say is that it's the one that has the switching have the most influence. Okay. There is also... I can't think of anything particularly interesting or different at exactly E bar equals omega that I've seen in any of my plots.
Okay, thank you.
I don't know.
So are there any online questions? So we have one online question.
So Morgan Lynch asks, if these are at 0.5C, can you examine the superluminal case and see Cherenkov emission and the anomalous Doppler effects?
I haven't considered that. I have looked at increasing the velocity, but that makes the numerics much harder. At V is greater than C, I imagine I would need some kind of structural change. The answer is no, I haven't looked at that. That's the simple answer. I imagine there would be some problems, some imaginary things popping out, something would go very wrong. It would be interesting to look at, though, but I have not.
Are there any other questions or comments from the room? If not, can we thank Adam once again for the talk and the plot?
Thank you very much.
Now, I'd like to welcome one of the co-organisers, Leo Parry, who will be talking about the circular motion under effect and other unruly-like effects.
Oh, that's going to happen a lot today.
At this point, I'd remind speakers to get the cable.
Yeah. Clip me in.
The floor is yours.
I have to press a button, Rick? Or... No, we're good? Okay. Yep, hello. My name is Leo Parry. I'm a second-year PhD student here at the University of Nottingham. And today I would like to speak to you about the circular motion Unruh effect and a related effect, which we call the drifted Rindler Unruh effect. And I'm going to show you that there are some similarities between the two. Okay, so I want to begin with some motivation, why we're interested in the circular motion Unruh effect here. First of all, the traditional Unruh effect says that a linearly accelerated observer will experience the Minkowski vacuum as a thermal state with temperature which is proportional to its to the observer's proper acceleration. However, it's never been observed, and partly for two fundamental reasons. The first one is that it's a very small effect. So, for example, as we often say, to get a temperature increase of 1 Kelvin requires your system to be accelerating at 10 to the 20 meters per second squared. The second reason is that it requires a very large lab. So here I have a picture of the Stanford Linear Accelerator, which is around 3.2 kilometers long. So if we had a system that was accelerating at 10 to the 20 meters per second squared, it would travel the length of this accelerator in around 3 microseconds. So it's a small effect and it requires a large lab. So how do we overcome these obstacles? Well, the first one is to look at analog systems instead. So creating precise mathematical maps between difficult to observe, complicated, not well understood systems, and systems that we can implement in tabletop experiments, for example, in condensed matter systems. So here we have a picture of, we call it the big tank here in Nottingham. So this is our analog black hole. The other thing we can do is look at circular motion instead of linear acceleration. So like linear acceleration, this involves a constant acceleration. However, now we can contain the system in a finite size laboratory for an arbitrarily long length of time. Okay, and what I was interested in, or what I'm interested in, is different types of stationary motion in Minkowski spacetime. So linear acceleration and circular motion are examples of stationary motion. A stationary world line is a world line whose geodesic interval depends only on the difference in proper time between points. They're also the orbits of time-like killing vector fields. And in this talk, I'm going to focus on three of the types of stationary motion in Minkowski. So we have circular motion, drifted Rindler motion, and semi-cubical parabolic motion. So circular motion, it has, of course, this circular spatial projection. It is the orbit of a time-like translation and a spatial rotation. And this drifted Rindler motion, here's the spatial projection. It's a catenary, so it's a hyperbolic cosine. It is the orbit of a boost and a transverse spatial translation. So you're accelerating in one direction and simultaneously drifting with a constant speed in a transverse direction. Hence, drifted Rindler. And then the final type of motion I want to talk about is called semi-cubical parabolic motion. And in the literature, it's also been referred to as the parator and possibly something else, maybe cusped or something. So this is the spatial projection. You can see it's cusped. It's a semi-cubical parabola. And it is the orbit of a time-like translation and a null rotation. So what I want to talk to you about today is the geometric relationship between these three types of motion and how this translates to the response of an Unruh DeWitt detector. So let's begin with the Unruh DeWitt detector model. So we consider a point-like two-level system. So here it has energy levels 0 and 1, and the difference in energies between the two levels is E. We refer to it as the energy gap. And we use this system as a detector to probe a massless real scalar field phi. And we allow this detector to travel along a stationary world line, x of tau. Tau is the proper time. And we couple the detector to the field along this world line via this interaction Hamiltonian. So lambda is a small coupling constant. Chi is a switching function which tells you how to switch on and switch off your interaction. Mu is the monopole moment operator, which induces excitations and de-excitations in the detector. And phi of x of tau is the field evaluated along the detector's world line. In this presentation, we're going to think about chi as essentially being 1. So we're going to think about an interaction that's been on from the asymptotic past to the asymptotic future. And in this limit, we can define a transition rate. So the rate at which this detector makes transitions between its levels. Here you can see it's the Fourier transform of the Whiteman function, which is the 2-point vacuum correlation function. Okay, good. And okay, I should say we refer to this transition rate as the response function. So once we have the response function, we can extract this notion of a temperature using this detailed balance formula here. So we take the ratio of the de-excitations and the excitations, and then we can pull out a temperature from this formula. So for example, if you have inertial motion, this formula will give you t equals 0. If you have linear acceleration, this formula will give you t equals a over 2 pi. However, in general, for stationary motion, this temperature will depend on the energy gap. To truly determine if your state is thermal or not, you would have to have access to arbitrary energy scales and say, well, this detailed balance formula holds at each energy level. In any practical setting, you only have access to a finite window of energies. And we say, well, if the temperature doesn't vary too much on any interval, then we can say we have this notion of an effective temperature, which can induce heating in your system. Okay, good. And okay, so let's talk about circular motion and drifted Rindler motion. Let's talk about the geometry. So here on the left, we have circular motion. I've written the orbit here. So circular motion and drifted Rindler motion are both described by precisely 2 parameters. So in the case of circular motion, I've written it in terms of the tangential speeds of the circular motion, and r is the radius of motion. Gamma is the gamma factor, and the acceleration is gamma squared v squared over r. In the case of drifted Rindler motion, again, I've written it in terms of a speed parameter and a distance parameter. In this case, v is no longer the speed of the spatial projection of the world line. It's this constant drift speed. And r is the distance of closest approach to the origin in this coordinate system. And then we can use this speed to define a gamma factor. It's no longer the real gamma factor of the world line, but it's a useful parameter in this case. And the acceleration in this case is gamma squared over r. So already you can see there are some similarities between the two. So in a hand-wavy way, we can say there's something like a v goes to 1 over v duality on the level of these orbits. So if you send v to 1 over v, Jorma, close your eyes for this part. Gamma goes to minus I v gamma. So you can see, so if you take, for example, is this the thing? Yeah, okay. If you take the third component of the drifted Rindler orbit, let's look at the first one first. So you have this hyperbolic sign of gamma over r tau. So gamma becomes minus I v gamma, and this hyperbolic sign becomes a normal sign. And this gamma becomes a gamma v, something like that, okay? So this first component becomes this third component here, right? If you look at the second component, again, this hyperbolic cosine becomes the normal cosine, and this gamma becomes gamma v, something like that. And then finally, this gamma v tau becomes something like gamma tau, right? So there's something going on here. This clearly isn't a proof, but there's something going on here, okay? So what is going on? Well, in this paper here, it was shown that circular motion and drifted Rindler motion have the same limiting behavior in the ultra-relativistic limit with fixed proper acceleration. They both become semi-cubical parabolic motion. So this is this cusped motion I was talking about before. So how does that work? Well, for example, let's start with circular motion. So here it is. We want to take the v goes to 1 limit with a fixed. So this means that the radius is going to tend to infinity. So the first thing we do is translate by the radius. And then we perform this boost in the t and y. So the t is coming out of the board here. So we're doing a boost in t and y, t and y. And so this is going to stretch the world line because the r is increasing. So it's going to stretch in this plane, this direction. And it's also going to be squashed due to length contraction in this direction. And you're going to have some movement along the y prime axis. And then if we take then the v goes to 1 limit, then most of these, all of these sort of coils go out to infinity, and we're just left with what happens at the origin, and it turns into this cusped motion. So this is the semi-cubical parabola. And we can do the same starting from drifted Rindler motion. So again, here's the hyperbolic cosine. We're sending v to 1 with a fixed. R again goes to infinity. So we're going to translate by r first. And then again, do this boost in t and y. And again, we get this contraction in t and y. And then finally, if we take the v goes to 1 limit, again, if you zoom in here, you get this cusp. Okay, well, we can do one better than this. We can actually deform continuously circular motion into drifted Rindler motion. So if we start with circular motion and we make this transformation that I told you about in the previous 2 slides to cusped motion, to semi-cubical parabolic motion. And then what we're going to do is we're going to define new variables. So we're going to define this new capital V, which is 1 over small v. We're going to define this new acceleration, which is capital gamma squared over r. Capital gamma is 1 over the square root of 1 minus capital V squared. And then we're going to allow this small v to vary on the interval 1 to infinity. So we've gone through the v goes to 1 limit. So if v is now varying between 1 and infinity, this means that our new big V is between 0 and 1. So it's our new speed parameter. And so if you then do the inverse of the transformation that I told you about on the previous slide, you boost back away from the ultra-relativistic limit and you get drifted Rindler motion. So starting with circular motion, you send V to 1, and then you send V past 1, and you can get drifted Rindler motion like this. Okay, so something like circular motion with speed v and proper acceleration a is dual to drifted Rindler motion with speed 1 over v and proper acceleration, okay, a at minus a, it doesn't matter. So the question is, does this geometric duality translate to the experience of a detector? Yes and no is the answer. So in the ultra-relativistic limit, we found that the response functions for drifted Rindler and circular motion are precisely the response function for the semi-cubical parabola. Okay? And then, of course, the temperature is the same as well. In the large gap limit, we find that the drifted Rindler temperature is between the traditional unroot temperature and pi over root 3 times the unroot temperature, whereas circular motion is between pi over root 3 times the unroot temperature and infinity. So, and this temperature here is, again, it's the temperature of the semi-cubical parabola, okay? Now, there's also the small gap, and it was found in this paper, which was done by lots of people here at Nottingham, that in this, if you consider 2 + 1 dimensions, circular motion, and you take the small gap limit, we find that the temperature is linearly proportional to the gap as e goes to 0. So we find that the temperature is vanishing as e goes to 0. So we asked, well, is this also true with drifted Rindler motion? Does it also vanish in the e goes to 0 limit? And we found that, no, it doesn't. It's a constant in the e goes to 0 limit. Okay, then we asked, well, does it happen in 3 + 1 dimensions? No, it doesn't. So the temperature is, again, a constant in the small gap limit. So, well, drifted Rindler? No, it's also a constant in the e goes to 0 limit. So then we asked, well, when does the small gap temperature vanish? Okay, so here, this is the response function in 2 + 1 dimensions. You can write it like this. So here I've taken out a factor of s on the top and a factor of s on the bottom. Now, we want to take the e goes to 0 limit of this expression here on the right. But in order to do that, we have to use the dominated convergence theorem, which, so we need to have this part of the, so this part is well behaved, right? This part is an integrable function. This part might not be well behaved, depending on the motion. Okay. So, for example, if this part dies as s goes to infinity, then we can take the e goes to 0 limit within the integral. However, if it doesn't, say, for example, if it's a constant as s goes to infinity, we first need to subtract this large S behavior. And this is precisely what happens with this with the circular motion. So delta x, say, for example, if we say delta x squared is of order s to the alpha as s goes to infinity, where alpha is greater than 2, then the response, so then this part is of order e by the dominated convergence theorem. And we have something like a quarter plus a term of order e. And this gives a temperature which has a 0th order contribution. So it's a constant as e goes to 0. However, if delta x squared is of order s squared as s goes to infinity, then this part here is of order 1 as s goes to infinity. So say, for example, if delta x squared is something like s squared over a squared, where a is a constant as s goes to infinity, then we have to add and subtract this a from this term before we take the e goes to 0 limit within the integral. And this gives us another 0th order correction to the response function, which depends on the sign of the gap, like this. Okay? So we have this is a 0th order contribution, and this is going to be of order e. So if we plug this into the detailed balance formula, we get that the temperature is proportional to the gap. Okay? So this only happens when delta x squared is of order s squared as s goes to infinity. So then the question is, well, which kind of motion has this property? So these are all the types of stationary motion in, well, I mean, we can forget about this one. This one doesn't exist in 2+1, the loxodrome. But let's think about these 5. We can ask, well, which of them has delta x squared is of order s squared as s goes to infinity? Well, the first one here is inertial motion, but inertial motion gives identically t is equal to 0, right? So we're not interested in that case. The only other one is circular motion. The other world lines, their delta x squared dies fast enough so that we can use the dominated convergence theorem. So this phenomenon is unique to circular motion in 2+1 dimensions. And yes, thank you for listening.
Thank you, Leo, for that talk. I want to open the room now to any questions that anyone has about trajectories to the underlying effects. Any from the wider audience? One from Perche.
Hi, thank you for your talk. I'm just wondering, this drifted Rindler motion, is there any experimental suggestion how it can be realized in lab?
I don't think so. I mean, it has the same problem that linear acceleration has, that it's just going to leave your whatever system you have almost immediately. I think the merit in this study is actually learning more about circular motion under effect. So this helped us understand the small gap limit of the circular motion under effect better. In itself, I don't think drifted Rindler has a lot of merit in terms of implementation in the lab. No.
Thank you. Are there any questions online? So it's interesting that the circular motion is the only bounded motion.
Yeah.
Arbitrary long interaction times also has this strange, characteristically different small energy gap limit. But I wanted to ask just, which is your favorite motion out of the 6 stationary trajectories in Euclid?
Well, I've been working with the drifted Rindler for a long time now, so I hate drifted Rindler. Favorite, I don't know. Is it vanilla to say inertial motion?
Yes.
Okay. Then loxodrome, the loxodrome, yeah.
Very good. Can we thank Leo once again? Wait, we have one question if you want to. We'll have to thank Leo a third time, but could you?
Sorry about that. In the 3+1 drift case, the energy gap is set by the transverse velocity dual to rotation, then you may be able to tune the energy gap using the rotation velocity. So in other words, drifted Rindler equals high energy channeling radiation. This is more of a comment, I would say.
Okay, I'm not sure I understood the comment fully, but saying the energy is determined by the speed?
This is perhaps better to discuss.
Okay, yeah, we can
Question
talk
for
about that later.
and, a thought to dwell on. So thanks, Leo, once again. And I'd like to welcome Cisco Gooding to the floor. And Cisco will be talking about quantum fields in analog spacetimes.
Thank you. Is that high enough up, or does it need to go? Does that work for volume? All right. Okay, thank you, Cameron, and everyone else for being here. This talk is going to be a little bit about the prototype situation, where we started exploring these analogies in a very concrete way to pull out signals, and this is the Unruh effect experiment. And what we can learn from that about other types of analog space-time effects that can be implemented in the lab and can potentially be connected to relativistic quantum information ideas. And so this is our beloved pancake. It's going to be representative of our favorite scenario where we have a relativistic 2+1 field, either a pancake BEC or a thin film of superfluid or just a surface wave. So as I mentioned, we have this prototype case, shooting lasers at a pancake and seeing if we could observe things like the Unruh effect with it. And the implementation of an Unruh DeWitt detector in those systems is going to be the most important thing that we could pull away from those, from this prototype, because it could be used for a lot of different contexts. So I'm going to describe some features about this setup and what we can take from that to apply to other RQI implementations. So to that effect, I'll talk a little bit about photon counting and photocurrents, and then a couple of words about the photon flux and power spectral density. In this respect, there will be some key differences between the predictions that are commonly used in optomechanics and the predictions that you would get if you just did the hardcore photon counting yourself. There's some disparities between these two predictions, and they've led to confusion in our collaboration for a number of years. So I'm going to point out things that we can learn from those, hopefully in a pedagogical way. And then just some words about analog RQI implementations other than the Unruh effect. Entanglement harvesting, maybe these area law conformations. These are collectively known by the acronym anarchy. So just a couple of words about the experimental setup for this Unruh effect in circular motion experiment. The basic idea is that in order to not destroy this pancake, we want to set up a laser that has equal contributions on both sides of an atomic resonance in our sample so that we don't destroy it. So it's basically just going to balance the Stark potentials that are acting on this system. And to do that, we put a single peak laser into a modulator, filter out the central peak, and then we have this two-peaked modulated laser that we shoot and deflect along a circular trajectory so that it traces out a point of interaction along a circle in our pancake. This is our PRL about that idea for the BEC. And then we showed that it could also be done in superfluid helium. And that's currently being implemented as we speak in Silke's gravity laboratory. A couple of just quick things about the photon counting. The two things we know about what's going to happen when we send this modulated laser into our photodetector, well, it's going to have an expected photocurrent that's going to be related to this combination of electric field amplitudes that are entering it. And here, these plus and minus superscripts just refer to the positive and negative components of that electric field that's entering the photocurrent. The most important one for the Unruh effect, because we want to be observing some signature of correlations that are sampled along this accelerated trajectory in this effective 2+1 relativistic field that get inserted into our laser field. We want to pull those out. So the unequal time correlator of that photo detection is really going to be the most important thing that we're going to look to see that signature. Unfortunately, the simplest way you do it, you throw that in, and you find that it, to leading order, gives you the exact wrong thing that you would like. You want the piece of this, what's called a Whiteman function, as the previous talks may have already indicated. You want the part of this that in 2+1 is imaginary. The straightforward calculation shows that you get, in that first leading order unequal time correlation, you get just the real part. This is a problem that has to be solved by either post-processing, spatial interferometry, or some other techniques. And I'll give one example of one thing that you could do to overcome that. Generally, we just have this photon flux that's entering our photodetectors. It's carrying a signal. We have some modulation at this capital omega frequency, and some electromagnetic quadratures that are sitting around. This one is related to common mode, and this one is a difference mode signal. This bit carries fluctuations from the pancake that we're going to use as a signature of our Unruh effect. Now, if we split this up into something that looks just like shot noise and something that's a signal plus some back action, then we can represent in our analysis of that operator, the photon flux operator, nice decompositions into pieces that we care about, pieces that we're trying to reduce, and pieces that just come along for the ride. So in optomechanics, they generally care about taking this photon flux operator and just assuming that it's the operator that we get to measure. If I measure it, I get some distribution of experimental outcomes, and from that, I can find all of the moments of this operator and just forget about the photo detection process altogether and only think about a single operator, its power spectrum, its moments, and so on. The problem with this, although you can get a long way into understanding the experiment, the problem with it is that it predicts that you get this response function popping out at the beat, around the beat frequency of this power spectrum for my photon flux operator. Now, we already know that that can't happen because the part that's non-zero of the Whiteman function, which when you Fourier transform to get the power spectrum, would give you this, that part vanishes. So there's an immediate disparity between the optomechanics prediction and the main quantity that they focus on, and the predictions of Glauber, which we know are the most accurate representation of what photo detection is modeled at. So this led to a problem that we're still resolving, or really still straightening out. It confused us for a while, but there are ways around this. So what can we do? One of the things we could do is autocorrelate the output signal. Instead of trying to extract everything just from the photo-detected signal-carrying laser that comes out of our sample, well, we can take the fact that Glauber predicts these unequal time correlations vanish for the thing that we want, take that piece of information and just work with it. Say, okay, well, I'll set up my own unequal time correlations by autocorrelating the signal. And then the Glauber probability for just the expected photocurrents coming out of each of these two output arms of the autocorrelator, they have unequal time correlations that give you the exact correct imaginary component of that Whiteman function. So this is one possibility. This delay line would have to be a fiber optic line that looped a tremendous number of times to achieve the correct time lapse for this. So this is just more a conceptual suggestion than anything else. But it gets the point across that really all we need to do is transform in a particular way using either spatial interferometry or other methods, and we can get different information that's in our signal manifest in those experimental signatures. Okay, now that the details of that UNRU experiment have been discussed, what else can we do with these kinds of detectors? One of the things you might imagine is just, well, what happens if we take two of them? Shoot them at this pancake in particular ways. The simplest one, just being non-accelerating paths, static points of intersection. Can we use this to probe other features of that effective quantum field? The implementation described here is for entanglement harvesting. And so the idea is I want to use my two continuous laser field detectors as detectors for that relativistic field and harvest entanglement that's in that field, either at very, very low temperatures so that I could consider it an effective vacuum, or potentially at higher temperatures where you have to battle a little bit of thermal noise, and there are thresholds that describe whether you can actually extract entanglement from those or not. It gets a little bit more complicated, but for now, just assume that I have a cold enough temperature that this is a vacuum, and I'm going to use these two lasers to steal entanglement from that field. Just like in the other experimental setup, these two beams are going to be prepared to have these dual peaks so that I don't destroy my pancake in the process. In superfluid helium, this is not quite as necessary. You have no atomic resonances that are really in the vicinity of these laser frequencies that we want to use, so we can ignore that for that purpose. But for BECs, it's a very helpful technique to minimize disturbance of the pancake. Anyway, this is just descriptions of how that beam preparation goes. The basic idea comes from the RQI community. Lots of people in the room know a lot about this from over the years. Yeah. And it's just like the model that we've seen before for the Unruh DeWitt detector, but we have a little bit extra structure. So we have a sum over J equals A and B for the two detectors, and now we have smearing over space, as well as the switching over time and the regular monopole moment that just has these two levels here depicted with an energy gap represented by capital omega. This smearing function basically just describes the spot size of the laser, and it limits the modes that your detector is sensitive to in the BEC or superfluid helium sample, and just does so in a self-consistent way. The causality issues that you usually get for extended rigid objects don't really apply here because the speed of propagation in your sample is so much slower than for the laser that they don't really come into play. But you still have to be careful about them. And so you could calculate RQI interested or quantities that the RQI community care about, like the negativity. This is just a generalization of the standard pair of Unruh DeWitt detector calculation, except I've included dispersion, because in any analog gravity experiment, you have a dispersive system that we're probing. So the field itself has dispersion, and we need to keep track of whether we're in the right regime so that we're probing the linear part of the dispersion relation so that it looks like an effective vacuum field, for instance. And these analyses, they tell you a couple of things about where you need to look in the parameter space to find this. They tell you, for instance, you get a maximal harvest of entanglement for times that are rather short compared to the energy gaps and the frequencies of the modes that you're probing, sub-cycle, which is surprising to me, but not really when you think about it. The details are, of course, well known in the community. but they actually do make it perfect for an implementation with these continuous laser fields if you use pulses. So instead of the continuous beams that have mostly monochromatic structure, this implementation requires pulses. So if you do the analysis of the experimental version of this with lasers, you find that you get effectively the same reduced density matrix structure if you neglect double excitations of individual detectors, but that doesn't actually contribute to the negativity to leading order. So effectively, they have the same type of structure. And this is a nice implementation to represent those simple cases of two under-DeWitt detectors. In terms of experimentation, this is the last thing I'm going to say about harvesting. It's a little bit more sensible to base your entanglement condition on something called the inseparability. There isn't really a finite time version of it to correspond to these pulses, but we're working to establish the validity and applicability of a finite time version. Basically, the idea is to measure variances of output quadratures of these two lasers and use that because it's so much more accessible experimentally to characterize whether you've stolen entanglement and how much entanglement you've stolen. And just in closing, there are a couple of last things I want to say about upcoming experiments. There's a really cool paper that Silke told us about that our collaborator in Vienna came out with very recently, Jörg Schmidtmeyer, verifying the area law using quantum simulators. And this is just another example of really cool information theoretic simulations that these cold atom systems open us up to. And a couple of just really cool things about this work. It's a one-dimensional quantum field that's being simulated, but you see this nice linear relationship between the von Neumann entropy associated with partitioning this thing and the length of the partition. So this is a volume entropy law that you would expect for thermal states. And the more significant one is the area law. Now, in one dimension, the area is a point, and you may say, okay, this is a constant, and that point has a constant area. What have you really shown? But it could have been anything else. They did show that it was a constant, and that point is a constant area, and okay, area law. Now the question is, can we do this for a pancake? Can we expand that idea to something that is potentially more rich in structure than the constant area? In the vacuum, for a flat space-time, maybe this would be interesting. Ultimately, for a vortex flow representing a curved space-time, there are lots of possibilities with this, and the techniques that Jörg and his collaborators have been coming up with could be really invaluable for those applications as well. And at that, I will say thank you for listening and acknowledge most of the people that have helped me in my life that I'm very grateful for.
Thank you, Cisco, for the talk, connecting all the theory that we're doing along with the experiments and with a future outlook for further experiments. Are there any questions in the room about anything Cisco has talked about today?
Other than the point area thing. We need Jörg to defend that one.
Or when we think about the future prospects evolving from a point law to a line law, I guess, in the pancake case. Are there any online questions? Then I would like to thank Cisco for your time today. And can we all give
Thank you.
So at this point, I'd like to welcome our next speaker, Silvia Schiattarella, who will be speaking in a joint talk with Sean Gregory on early universal phenomena in fluid dynamical effective
Like this?
theory simulators.
Yeah? Okay. Thank you very much, Cameron. Okay.
The floor is yours.
Thanks. Okay, so today I'm going to briefly introduce the work that me, Sean, and other people in the group like Vitor are carrying out in the gravity laboratory that is about analog cosmology. With this work, what we propose is a classical to fluid system that we use as an analog model to examine some of the effects of the preheating phase of the early universe. I'm going to now just give a general idea of the, of the cosmological background by starting with the reheating. Reheating is a phase of the cosmological scenario during which is a process that describes basically the production of the particles of the standard model. And this process takes place right after the exponential expansion represented by inflation. So basically, at this stage, what happens is that the inflaton field leaves the flat region of its potential and starts oscillating around its minimum. In this region, the inflaton field will transfer its energy density to the other scalar fields coupled to it. And in particular, if this process happens by inducing parametric resonance in these modes, then we have preheating, the so-called preheating. So basically, basically what we see is that the amplitude of these modes are going to increase exponentially through time, which means on a physical level that we have a rapid production of particles. The theory of preheating, what we expect to see for this theory is that initially, we will observe the exponential growth of a primary mode. Then that primary mode will decay in the production of secondary modes, secondary stabilities, which means basically that there is a even bigger production of particles that will lead the universe towards thermalization. We aim to observe exactly this kind of effects. In order to do that, though, since we are not able to observe directly this kind of phenomena, we have to use an expedient. This expedient is given by analog cosmology in this case, which allows us to reproduce some of the key aspects of these cosmological scenarios in laboratory-based experimental setups like the one that I'm going to describe here. Okay, so I want to now stress why it's possible to make this connection between the fluid system and the cosmological theory. What happens is that the analogy is based on the presence in both systems of this parametric resonance. Parametric resonance is a phenomenon that happens when we when a system exhibits instabilities when subjected to an external periodic force. In particular, if we linearize the solution of this motion, we obtain Mathieu's equation. And Mathieu's equation is central for our study. In fact, it describes exactly how, on one side, the interaction between the inflaton field and the fields coupled to it happen. And on the other side, how the dynamics of the azimuthal modes on a fluid system will evolve, basically. And of course, we're considering a fluid system that is subjected to an external periodic force, and we will see the appearance of Faraday waves, modes or instabilities that will be parametrically amplified. A couple of words about our setup. So our setup is composed by a biphasic solution of with aqueous phase and organic phase. These two fluids have different densities, and such that basically if we mix them after a while, what happens is that they're going to separate out, and in particular the organic phase is going to sit on top of the aqueous phase by creating an interface between them. Then what we do is to drive externally and oscillate vertically this system, and what we study is exactly the dynamics of this interface between the two fluids. In particular, we're going to study its dynamics in the nonlinear region, such that we can have some more insight, learn something about preheating as well. Okay, so here we have a picture that represents a reconstruction of data from our system, where we see that the top fluid, the lightest fluid, is transparent, basically. Okay, now some about the observations that we had. Okay, here there is a plot that shows the behavior of the amplitude of the primary mode respect to time. And we see distinctly the different stages of our experiment. So we start from an initial phase where the detection scheme noise is overwhelming the whole signal. Then we start driving externally our vessel. And what happens is here, as you can see here, this primary mode will be excited and will undergo parametric resonance and exponential growth. But this growth doesn't last indefinitely. In fact, the system will reach at a certain point this. Okay, I think it might be out of. Okay, well. It reaches the nonlinear regime where the different modes in the fluid system will start interacting with each other. And in this phase, the approximation we made to obtain Mathieu's equation are not valid anymore. So we observe breakdown of the parametric instabilities, and basically what happens is that the amplitude of the primary mode will stabilize. And this mode will decay, let's say, in the excitation of the secondary modes. Finally, we will have that in this red region, that we shut off the external force, and the excited mode will decay back to equilibrium. So now, to just conclude, basically what we observed through this research is that we're able to observe some of the key features of the preheating cosmological scenario by reproducing them on a hydrodynamical system composed by two fluids. And Sean now is going to briefly talk about our current goals, which is basically to reproduce some of the other characteristic aspects of different cosmological scenarios, such as the thermalization of the universe, or what happens if we apply an external magnetic field on our setup. So, yeah, that's it. Thank you. Welcome. Oh, yeah. Yeah, we'll answer the questions later, I think. Have to just like this. That's okay.
Cool. Okay. So now I'm going to talk a bit about what we've been using our experimental setup for, and that is the study of universal scaling dynamics. So I'm going to tell you a bit about what that means. Say we have some system that we prepare in a sufficiently far from equilibrium initial state and then leave it to thermalize. It will pass through an intermediate period of self-similar evolution that we call the scaling regime. Now, the scaling regime is a fixed point attractor solution, meaning that so long as the initial conditions were far enough away from thermal equilibrium, it will pass through the same scaling regime regardless of the details. This insensitivity to the exact details of the initial conditions are where we start to see the effective loss of information during the thermalization process. So what are these self-similar scaling dynamics, other than a bit of a mouthful to say? Well, these are dynamics that can be effectively described by a simple scaling relation. For a homogeneous and isotropic system, the relevant scaling relation is the one here, where these alpha and beta are called the scaling parameters, which are parameters which have some relationship that depends on the details of the system. Now, I've only had to tell you that the system is homogeneous and isotropic in order to specify this form of the equation. And as such, we expect this equation to apply to a wide variety of physical systems. This is the concept of universality, and universality is what we exploit in analog cosmology. So in our case, we expect to see the same dynamics occur both in cosmological preheating as we do in the nonlinear evolution of our interfacial modes in our fluid mechanics experiment. And of course, a fluid mechanics experiment is far more accessible than scalar fields in the early universe. So not only is it a fantastic test ground for understanding general phenomena, but it also gives us an insight into the cosmological scenario. So here's what scaling dynamics look like in practice. On the left, we have a graph showing some simulated data for a free two-dimensional system. We see that at low momentum scales, the distribution function follows a power law behavior, whilst at high momentum scales, it deviates away from this power law. We also see that during the scaling regime, the distribution function decreases with time at the low momenta, whilst increasing with time at the high momentum scales, as energy is transported up to the higher momentum scales in the system. We can verify that this is indeed described by the scaling relation on the previous slide by rescaling the momentum along the x-axis and the distribution function on the y-axis by these factors of time over some reference time raised to the power of alpha and beta respectively. Doing so collapses the distribution function plotted at different times into a single curve, as can be seen up the top right here. So this is what we're currently looking for in our experiment. The last thing that I'd like to talk about is our future plan for improving upon our experiment. So specifically, we want to apply a magnetic field across our interface in order to study an expanding space-time background. So why do we want to do this? Well, our current experiment simulates a scalar field theory on a 2+1 dimensional Minkowski space-time. Now, this is conformally equivalent to the equation of motion for a scalar field theory on an expanding FLRW space-time once we redefine the field to incorporate the scale factor and work in conformal time rather than physical time. So this is great because we can learn something about the expanding cosmological case by looking at an effective metric that's stationary. However, the details of the expansion are obscured in this mapping. So this is because we're working in laboratory time for our experiment, which serves as an analogue for the conformal time and not the physical time. So we can't see any inherent effects of the expansion of the universe, such as, for instance, mode freezing upon horizon exit. In order to do so, we need an explicitly expanding background. But this seems very challenging, right? How can we somehow expand the size of the vessel of our container mid-experiment whilst also keeping the balance between the two fluids just right so that the interface maintains intact? Well, fortunately, we don't need to do this. We have a clever workaround which relies on the fact that the expansion of space is equivalent to the slowing of the speed of light. Now, that may seem confusing at first, but let's take a look at the Minkowski metric, where we have modified the speed of light to be time-dependent. If we identify this time-dependent speed of light with the reciprocal of the scale factor, we can pull it out the front as a global factor such that the effective metric now reads as the FLRW metric up to a global factor of 1 over a squared. In our system, the wave propagation speed is our analogy to the speed of light. So if we find a way to make this wave propagation speed time-dependent, we can produce a system with a FLRW effective metric. The way we're planning on doing this is to replace the upper fluid with a diamagnetic material, the lower fluid with a paramagnetic material, and then to apply a strong magnetic field in the radial direction across the interface. Doing this introduces a magnetic potential term in the Euler momentum equation that governs the dynamics of the interface. The magnetic field will be produced by an electromagnet that we have a high degree of control over. So by changing this through time, we make the magnetic potential time-dependent also. This in turn induces a time dependence on the wave propagation speed in the subsequent equations of motion. By doing so, we can create a system with an effective FLRW metric of an expanding spacetime. So to summarise what we've talked about, here at Nottingham, we are simulating a 2+1 dimensional effective field theory by using the interface between two fluids of different densities. We can induce parametric resonance on this interface in order to study cosmological preheating. The specific aspect of cosmological preheating that we are currently interested in is that of universal scaling dynamics. And finally, we have future plans to upgrade our experiment in order to simulate a more realistic cosmological scenario. So thank you very much for listening, and let us know if you have any questions.
So I'd like to thank you, Sean, and to thank Silvia for that talk. And I'd like to open up the room to any questions. Although I think I'll kick it off by, so the principles of universal scaling relied on the isotropy and homogeneity, which are also the underlying principles of Friedman cosmology. So if you see this, or when you see this universal scaling in the first setup, do you have any intuition how this might change when you introduce this magnetic field across it?
That's a good question, actually. We haven't considered that.
Yeah, exactly.
Yeah.
More of an outlook question.
Yeah.
How would that change?
I don't know.
Will it still be isotropic and homogeneous? Maybe.
I don't think it'll be isotropic anymore because there's a strong gradient to the magnetic field, so we are ruining the
Okay.
Yeah, that's actually what we want to study a bit to understand how, because we have to understand also like what are the conditions of the magnet that we want to introduce, the geometry of the vessel itself. So it's probably something that we will figure out while, yeah.
Okay,
yeah.
Perfect. And are there any other questions in the room? Patrick?
Thank you for your talk. So in order to study these inflationary scenarios or parametric resonances, you observe some exponential growth, right? Which means that you have to probe your fluid cell across many orders of magnitude. Could you comment on that? Like what is your accuracy in detecting these interface waves in time? How many orders of magnitude can you actually cross? And also, what is the smallest length scale and the largest length scale that you can probe?
Well, we can see down to the micron limit, and we have quite high time resolution. That's one of the benefits of our system compared to other similar analog cosmology experiments. So we have 100 frames per second on our camera, which gives us a high degree of time resolution that you can't get in, say, a quantum system that's serving as an analog to the same cosmological effect.
The other thing that I want to add is just that, for example, when we study the parametric resonance, so this exponential growth, what happens is that basically what we see for the primary mode is that mode is of the order of maybe 10 to the 4 microns or something like this, a bit more than that. And usually the difference between the primary mode and the secondary is a couple of order of magnitude. So we have something of that size, I would say, in general. But as Sean was saying already, our resolution in that sense is around the micron, something like 40 microns, maybe, exactly, something like that. And more or less is that. And actually that created a couple of problems for us until now, because we wanted to, for studying this cell-similar behavior, we have to resolve as many modes as we can. And so we need all modes that have some kind of like decent amplitude that we can actually observe and say something about. So yeah, that's a good question. Thank you.
Thank you. And if no other questions, we have one.
You mentioned changing the speed of light as being analogous to the universe expanding.
Yeah.
Is that something that applies to your system, or is that just a global interpretation of the expansion of the universe?
That's a general interpretation from if we see the metric here. So this doesn't have to be necessarily an effective metric. If we did somehow have a time-dependent speed of light, we wouldn't be able to tell that apart from the expansion of space, essentially.
Thank you. And if we'd like to thank Sean and Silvia once again. Thank you. And with that talk, we've made our transition from the theory into the experimental side. And so in the second half, we'll be talking mainly about our experiments. But before that break, we have our career development talk. And this will be hosted by Sally Hall and David Hawker. So if I'd like to invite Sally to the front.
Wherever you like. Is that okay? It is, yeah. So no clicker, just the... Okay, brilliant.
Thank you.
Thank you so much. So we're moving on briefly to something rather simpler, I think, in many ways, but which many of us can find quite challenging, and that's the careers context, and particularly looking at making applications. My name's Sally Hall, and I'm the careers consultant for the Faculty of Science in the University of Nottingham. I'm actually here on behalf of my colleague Kirsten Barnard, who is the PGR Careers Advisor within the Careers Service. And the reason why I think, doing this is because everybody has to think about their next steps at some point. Is there a quick show of hands in the room? Anybody who's been giving any thought to what their next steps after their current, what you're currently doing? Anybody who's giving a bit of thought to that? Yeah? Excellent, thank you. And so in any process of thinking about those next steps, you're going to have to, at some point, get down to putting together a really strong application. So what I'm doing today is just giving some overviews around that, most of which I would hope you'd kind of recognise, but also pointing you to some useful resources. So I'm going to focus mainly on academic applications, but with an reference to industry routes, because many PhD students and early researchers will go out to careers in industry, and it's a perfectly valid route to be considering. So like I said, headline guidance in terms of signposting to resources and support. In terms of what comes before the applications, unsurprisingly, there is that thinking that you need to give to why are you going for things, what's your motivation, what are you interested in, what are your key skills, your achievements, what are your strengths. And if you're not quite sure about that, because sometimes when we're asked that question, what you're good at, what you enjoy, there are some obvious things in terms of your subject matter, but perhaps it can be hard sometimes to think more broadly about that if you're going to articulate your skills and strengths in an application form. So I'm just going to pop all those up there. So some key components of career thinking and choosing your next steps are about understanding those things around yourself, but also about what's out there. And sometimes maybe within academia you think, well, this is just an obvious step, or I take what's, the first thing that comes along, I don't know. But it's important to be able to step back and to actually think about what do you want, where are you at so far, what's been really satisfying, what have you really enjoyed, which bits are you not really keen on, what would you rather not be spending some of your time on. And those are the sorts of things to be thinking about before you start to then search for and apply for opportunities. And they may be roles in academia, you may look wider or be curious about roles in industry. You may be looking for what's out there that's directly related to your key areas of research interest. And just flagging up that there'll be a range of role titles out there and many more, I am sure. So they'll be thinking about what can further your career in the context of what sort of direction do you want your career to go in terms of what you want to be doing, what you want to be getting out of it, what impact you want to have. Those are just some of the sorts of questions to be asking yourself before you get to actually putting together an application. So in terms of academic CVs, I suspect this won't be new to you, so I'm not going to go on in great detail about everything that's in the slides. But for academic applications, clearly you're going to set out your research activities, publications, and funding awarded. They are definitely longer than industry CVs, which is a rule of thumb. We might talk about sort of 2 pages for an industry CV, whereas with your academic CV, you can go into, and you need to go into, much more detail. There is a commonality, no matter whether you're applying within academia or industry, in that you do need to make it really easy for the person reading it to actually quickly be able to see the key points and evidence that you want them to pick up that are relevant to the role that you're going for. So your research activity and techniques, publications, your funding awarded. In some cases, I'm aware that maybe there are sort of works that are due to be published, but not yet, or maybe there's a reason why you can't yet publish. So those are things that you can set out in your CV. And we have included in here also a reference to something that often can sometimes concern people if they've taken a break for whatever reason. It's okay to make a reference to it. You just keep it brief, keep it factual. Just make sure that you're not just leaving a big gap in your CV. Okay. So in terms of academic CVs, again, keep jargon to a minimum, but writing with clarity is going to be really important. This is about presenting your evidence really clearly, so making sure you're including all the key things around your qualifications, research, publications, and your contributions to them, and spelling out, are they sort of journal articles, books, chapters, etc. When it comes to research experience, making sure that you are actually pulling out all the relevant components in terms of the activities, the skills that you've demonstrated, which may be about your technical skills, but also about those wider transferable skills that are essential in any role, including roles in academia. By the way, if anybody wants to interrupt at any point, I'm happy to take questions as we go along. So the next couple of slides are things that you can very easily also find on websites like Vitae, and we've got the link to that on here. So this is just either a reminder or maybe an introduction to some of the things to be thinking about in terms of your academic CV. So making sure you've got your education listed clearly, reverse chronological order, or your funding details in there. Teaching experience is often going to be maybe something that's required for one of the roles that you go for. So making sure that you give good information about the nature of your teaching experience. And even if it's limited, then you can still think about all those different components of things that you've done that have either been delivered directly in direct teaching experience or that are related to it, whether that's kind of the organisation and planning of materials, for example. Other areas then, as you get into academia, administrative experience and admin roles and things that relate to, you've got here sort of examples of committee membership, course organisation, those sorts of things. But within academia, as you probably know, there are always other things that come within the role or as part and parcel, or you'll be asked to do as part of your expanded or extended role. So make sure that you actually put those other areas of experience onto your CV. Other things on there I'm not going to go through. You can easily read those, and like I say, they are clearly listed in guidelines on the web, the resources that I will share with you also. But I would reiterate the really obvious thing at the bottom in terms of asking somebody to read through what you've put together. Even the best of us benefit from somebody else having a look at it, giving some feedback, whether that's coming to see a careers advisor, whether it's a trusted friend, no matter what, always make sure that you do that. Okay. Most of the time in some form or other, you're going to have to do something that is called a cover letter or basically is asking the same things as a cover letter. And again, if you're thinking about roles in industry, same things apply. The main focus is in actually thinking about your audience and thinking about demonstrating why. Why do you actually want this role within this university, within this organisation, doing this particular sort of piece of research or this particular activity. So how can you actually showcase what you've done and the skills and the strengths that you've got and how that relates to the research project or role that you're applying for? So really trying to set out what the fit is and demonstrating that you've done your homework and you really understand what it is that you're applying for, the piece of research, and that you've perhaps gone the extra mile in terms of maybe having those conversations with the research supervisor or somebody in an industry role sort of who can give you some more insights into that role and activities. this is just kind of reinforcing it, because we just can't reinforce it enough, that you do need to be able to customize your application, and within your cover letter, making sure that you really are spelling out, for example, how your background is aligned to the principal investigator studies and what's being asked for. And think about, why do you want the role? Because you're going to be asked. You're going to be asked at some point, and you need to be able to articulate it with some strong evidence that demonstrates your understanding of the role and activity, and how your strengths and skills and experience are a really great fit for it. We've put in enthusiasm in there. You can convey that absolutely through your cover letter and application forms, and then obviously you'll get the opportunity to do much more than that when you get to an interview stage. So I think that's probably, I feel like I've done a bit of overkill really on the connecting bit. It's kind of more reinforcement of some of the things that I've already been talking about, but perhaps making a few more specific and explicit sort of observations. So if you are moving into something slightly different, then you need to be able to explain that and demonstrate how that interest has come about, and sort of give a reasoned evidence for that. The last bits on here are about, again, doing those things that perhaps are really showing your commitment to it and sort of genuine interest in the opportunity by what you've done in terms of your sort of conferences you've been to, reading you've done, people you've spoken to, so that you can kind of you can really kind of convince them of your interest levels and capabilities. Applications and sort of come in all sorts of, so sometimes you might be asked for a CV and a cover letter, sometimes it's an application form. It basically comes down to the same thing in terms of presenting your evidence. The application form process might ask for a statement of research interests, proposing future research, how does that build upon your current expertise. So research aims, achievements, techniques, and your responsibilities are kind of key things and components to think about for application forms. We do reference a variety of examples, using a variety of examples. That may seem very obvious, but sometimes we can kind of sometimes find that we've been using the same thing sort of, and just kind of variations on that all the way through. And you need to give a reasonable breadth of evidence in your applications. So there are maybe some questions you might get asked that it's as well to be thinking about sooner rather than later. So it's back to the motivation questions about why. You know, why do you want this role? Why this institution? Why now? And so it's thinking about what is a kind of logical sequence that demonstrates and authenticates my interest and motivation for this role. The sequence there is just showing that sequence. And that sequence could include that you have switched and changed a little bit in terms of direction. But by giving that kind of sequence and underpinning to that, then you can demonstrate the validity and the rationale behind your journey to this stage. You may be asked about particular skills like teaching experience or teamwork, as those are always going to be important things. Possibly things like when you've demonstrated resilience, and I'm guessing most of you will have some good examples for that. You're here now, so that's one good one perhaps. And we always reference the STAR technique, which some of you may be familiar with. Anybody kind of nod if you're familiar with it? It's a very simple, basic one, makes sense. Situation, task, action and result. So if you're asked an interview question about an example of your teaching skill, or a time when you collaborated with others for a common shared goal, then what they're most interested in and what you did. So the action bit of it will be sort of like 70% of your response, but you need to set out clearly the situation, So at this university, in this team, in this department, we were asked to do X, the task involved whatever it was, and this is what I did, and that's where the majority of your answer comes in. The result bit is what was the outcome, and you could add in a reflection also in terms of what worked well or what you learned from it and that you might do differently. And the reason that's helpful is because it can help you to avoid going down a pathway of lots and lots and lots of description and explanation, and the person interviewing is waiting for the actual evidence or struggling to actually sift out the evidence from everything that you've said. So it's a structure that gives some logic to it and reminds you where the majority of the information should go in terms of what you did, because that's the key evidence. And that's just reiterating specific examples. So never go down the kind of, well, I've done lots of teaching and I generally tend to do this and I find it helpful to do that. Always come back and give a specific example of something that you've done. So these last slides are just a kind of reminder of industry routes are out there also for those of you who may be contemplating that, however vaguely. And these are from our University of Nottingham careers web pages, which gives you information about careers outside academia and application processes and guidance. And again, for University of Nottingham PhD students and early careers researchers, then that's just flagging up the appointments on offer for you and what you can gain from those appointments in terms of support with applications, but also strengths coaching to help you think about your strengths, motivations and interests. Resources include where to look for jobs and also things like VTI, which has got lots of guidance on applications and application processes. And again, for Nottingham students and early careers researchers, that's how to find us in terms of making appointments. I realised I was trying to gallop through the last bit because I've probably taken up time, so I'll either take questions now or hand over.
So if we can all thank Sally for the talk. Are there any immediate questions? I'll take one from Mr. Patrick.
Thank you. I would like to ask, there is this new format of resumes called Resume for Research and Innovation, also called these narrative CVs. Do you have any resources for that? Because these resumes are now currently mandatory for some grant applications.
I think we do. What I can do is share that. So are you sharing some resources after? Okay. All right.
Chip into that one as well. We're actually running a training session precisely on narrative CVs, which is due to happen. I think it's about 3 weeks' time. We're just putting the registration form together today, actually. So we're hoping to send it around early next week.
Awesome.
Perfect.
So obviously, if you're in Nottingham, you can take advantage of that. If you're not at Nottingham, I'm sure we can arrange to send one to you.
That sounds even better. Okay.
As a quick follow-up, if they don't mention that they're looking for a narrative CV, is it getting to the point where we should just assume that that's what they're looking for? Or is it, still...
They're normally pretty clear about what they want, so I would say that unless they specifically ask for one, you'd go with the more traditional route. Because, most of the UK funders have kind of adopted it, but by no means all. So there's still some that kind of still go the old-fashioned way, and a lot of the international ones will still be that way as well. Okay. So, yeah. Thank you.
Fair point.
Okay. I believe we had one online question.
So, as a question for prospective PhD students, how does the fees and funding work for PhD students, and in particular for international students?
So I'm not going to be the expert on that. Somebody else might want to come in, and yes, because there certainly are differences.
They vary massively.
Yeah.
The stipend, if you're lucky enough to get a funded studentship, then the stipends are fairly kind of standard across the UK, because they normally match the sort of government set base rate, which is, I can't remember the exact number, but something around 20,000 a year. The fees, though, they vary between every institution. institution, between every course at an institution, and the international fees are enormous compared to the UK level fees. So whereas a UK person might be paying sort of £4,000 or £5,000 a year, the international person might be paying £15,000 to £20,000 a year.
But that would be covered by funding?
Well, so this is it. So most of the studentships that are available in this country will only fund at UK level. So if you're applying from an international, somewhere international, then you'll be expected to cover the difference in international fees, which is quite substantial, of course. Occasionally there are kind of institutional-based schemes. So there is a Nottigham Vice-Chancellor's Award, which gives out a very, very limited number of international scholarships, like, 2, 3 year kind of numbers. And the other institutions have similar things, but the vast majority of the time the applicant is to be lumbered with it. So unless they've got government sponsorships, or sometimes, particularly from the Middle East, they do. Sorry. In the Middle East, quite often their government sends over a cohort of people and they'll pay for it themselves. Right. But most countries, of course, won't do that. So they're left with footing the bill individually, unfortunately.
So is that the case for most of the international students on a PhD here?
Yeah, absolutely. And I mean, even if we secure funding from grants or other sources, even those most of the time will only support UK level fees as well. So if we've got like a doctoral training centre or something like that, again, same applies. So it's very rare we get any international sort of level scholarships. So yeah.
Thank you. So if we could thank Sally once more and welcome David to the floor.
Yeah, please do. Okay, thank you. I'll try and keep mine short, because I know there's a refreshment break coming up. So.
And the floor is yours.
Lovely, thank you. There we go. It's trying. There we go. Okay, so I'm just going to add on a few things. I was asked to cover a few sort of questions by the organisers. Some of mine things have got links in, which will obviously take you to some more information if you want to follow up on them. Well, obviously, if you've got any questions at the end, feel free to chip in. So these are the kind of things I'll briefly talk about. So if you're not applying for a job, or if you want to consider some other options, there are fellowships, so I'll say a bit about those. Generally, what the practicalities are you going to end up with an academic career or not? What are the salaries of postdoc positions, and some bit about visa information. So the first one, personal fellowships. So there's quite a lot of schemes available in the UK and internationally. They'll be varying in terms of their eligibility criteria, so they might be set for certain years post-PhD levels of experience, for example, or they might have restrictions for EDI, so some are aimed at women, for example. Others will be in specific fields. But they all kind of follow a general principle that they're looking for people who've shown a level of independence. So if you come out of your PhD and all of your publications are with your supervisor, for example, and you don't have any other sort of activity on the side, it'd be quite difficult to pursue a fellowship. On the other hand, if you come out of your PhD and you've got 2 or 3 sole author publications, or ones where you can demonstrate that you've driven the content of those papers, and you've maybe organised some workshops like this, or done some other activities, outreach or whatever it might be, where you've kind of gone that extra mile to get away from what necessarily your supervisor has told you to do, then you're kind of on the route towards that kind of fellowship sort of mindset. So it might be that you're in a position to do that after your PhD, or it might be a couple of years down the line after sort of a postdoc appointment or 2. But if you get to a point where you've got a strong list of publications and other bits and pieces, and you've got overall a strong idea for what you want to do as a research project that you've come up with and driven yourself, then there's an enormous list of fellowships you can go for, and there's a URL there you can have a look at in your own time to see the various options available. Most of them will be funded by some branch or other of UKRI, which is the main government funder. There'll be others that are listed by societies and charities and so on. The main thing I would say is always read the guidelines carefully, because they do change year on year, and the scope changes, the eligibility changes. If you're not sure, you can't interpret some of them, you don't understand what's meant by a certain paragraph, then come and speak to me, or come and speak to Silke or equivalents at other institutions. Do obviously speak to potential hosts. So although it's your own kind of project you're driving for a fellowship, it is expected that you'll work with the host department or potential host department and one or other sort of academic mentor there that can kind of give you that information to say, yes, we will support your application. Yes, you're a good strategic fit to our institution, to our department. And that information is quite often required by the funders in addition to your own kind of project. But I guess the main message anyway is come and speak to us if that's something you're interested in, and we can give you a lot of advice and we can help out with your CV as well as the Careers Office can as well. So what is the actual reality of where you might be ended up? This is a great diagram that I like to trawl out in these sort of presentations that the Royal Society did about 10 years ago. And they did a massive survey of researchers across the UK to kind of determine where they ended up after PhD. So you can see where it starts. It divides into people who kind of immediately left any sort of scientific research, which immediately divides into two. When you get into kind of the first postdoc, it kind of goes down to about 30%, with the rest going off into industry. And as you can see, the further you get down the line, it shrinks and shrinks and shrinks. So by the time you get to people who've actually realised a full professor position, it's pretty tiny. And most of that is purely just because of available positions. So if you think about, when you start off undergraduate cohort, you've got 300 other people in the room. By the time you get through to masters, it's maybe 30 people in the room. By the time you get ready to PhD, it shrinks further and further and further and further and further. And in practice, a lot of people will not make it that far. And it's not necessarily due to a lack of quality, it's just there's just a lot of competition for what's available. If you do get something like a personal fellowship early on, that will stand you in pretty good stead for pursuing an academic career, but by no means that's the only kind of tick box. A lot of people simply get frustrated or demotivated after a certain amount of times in postdoc and say, well, I've had enough of this, I'm going off into industry, earn some more money or whatever it might be. And that's perfectly fine. And what I would say is there's no right or wrong path. Just if you've got an idea in mind, where you want to be, then by all means, obviously go for it. But don't, as if you were going to be a pop star, don't expect you necessarily get there. The trying is excellent, but don't put all your hopes on actually achieving it. There are numerous roles in higher education institutes that you can fall back on if you do have a PhD. So technicians is one, particularly if you're in a sort of lab-based kind of studies anyway. Things like what I do. So I did a PhD many years ago in maths, and I've ended up here. In my defence, it was because I got bored of research straight after finishing my PhD, but in any case, there's many other people who do roles like mine, and most of whom will have either a master's or a PhD in some subject that may or may not be relevant to what they do at the moment. There's various other people that work on sort of more business-facing things, trying to get money from industry into the university, and most of those will have some sort of higher degree. So if you're interested in those kind of roles, but obviously by all means come and talk to us as well. And it's worth investigating if you do like the academic sort of environment but aren't necessarily interested in pursuing research in the long term. But that's kind of the reality anyway. Salary. So this is the crunch figures. This is all based on numbers at Nottingham. So obviously it will vary around the UK. So in London particularly, you'll have quite a bigger salary, but then of course the cost of living there are substantially higher as well. So the typical salary for a postdoc here is in that range. That is normally one where you're kind of somewhere between having just finished your PhD, in which case you'll be at the lower end of that, or you've maybe got one position under your belt already, in which case you'll be maybe 2 or 3 points up there. If you go for a sort of senior fellowship, which is typically one that's sort of 5 years duration, or there's just happens to be a really highfalutin postdoc position out there, then it might go up to the next scale up, which is 50, 40, sort of 50 sort of range. To put that into some sort of perspective in terms of quality of life and costs in the UK, this is a stat I retrieved yesterday from Joseph Rowntree Foundation, which is accurate as of about a month ago. So you can see that a single person would need about 29,500-ish. So if you get the sort of base level postdoc, you'll be just about comfortable, is I guess the main message to take home there. If you get a bit better, or if you get a fellowship, you'll be flying, buying chocolate for everybody in the department, probably. I guess the main message is you'll generally be okay if you manage to secure a postdoc position. It obviously gets easier as time goes by and your salary goes up a bit. But if you do have a chance to get married and have a couple of children, it might be I wouldn't necessarily recommend that, having done that myself. Anyway, the employment benefits are fairly standard, I would say, across academia in this country. The hours might vary slightly and pension allowances might vary slightly. But most of the larger universities in this country are in the same pension scheme, and we get a certain number of days allowance that's pretty standard across the board. I mean, generally I would say it's pretty good allowances. You're obviously aware that there's a lot of issues about the pension scheme, and I've been for a few years, but still compared to most private sector roles in this country, it's still pretty good, you'd have to say. And finally, some visa bits and pieces. It's a fairly easy one, actually. So whether or not you're going for a postdoc or a fellowship, regardless of what it is, you'll be after a global talent visa to stay in the UK. And there's some links there. And the good thing is we've got a dedicated visa staff immigration team in this university who can give you all the advice with that. And they also help with things like adjusting to life in the UK and cultural differences and things like that. And there's some little bit of practicality detail there. So you can obviously look at those slides in your own time, and I won't go into massive details of anything else, but obviously if you've got any immediate questions now, happy to take them. But that's it. Yeah.
We'd like to thank you first. It's more of a comment/question.
Yeah.
I've heard of cases actually the university is not really sponsoring global talent visa. I'm starting a postdoc and starting with skilled worker.
Okay.
It's just does the university hope to make it into an actual permanent thing? Because it has implications also. It's a better type of visa to be in, right? Than a skilled worker.
So it should be the case that any postdoc that's recruited to a funded position. So most postdocs will be appointed to something that's funded by a research grant. Almost by definition, they're a global talent visa because there's a category of researcher that's essentially funded researcher from, and it's needed because they've got a specific set of skills. Slightly different argument for fellowships, but basically the end result is the same. That because they've demonstrated their exceptional ability, they've won their own funding to stay in the UK with a particular host, and therefore they're eligible for a global talent visa. There are some other categories, as you say, but yeah, that would be very much a case-by-case basis where it doesn't fall into those two categories, but the vast majority should fall into those two categories. So.
Thank you. And we have two more questions in the room. First, Patrick. Thank you. I was quite intrigued by the whole chart where you were.
I like it, yeah.
I'm just wondering, does this take the whole academic sector, or is it somehow specific, compared to between natural and social sciences or engineering and so on?
The survey they did particularly for that diagram was STEM, so it was across science, technology, engineering, medicine, just because that's kind of the remit of the Royal Society. And it's, I would say, broadly the same across any academic subject, and probably internationally as well as UK. I mean, that diagram is very useful, but I've read other articles and things which say pretty much the same thing.
The IOP has its own chart like that, right? And it's similar figures.
Yeah.
Only for physics.
Yeah. Mm.
Thank you. And we have another two more questions in the room. First, Patrick. Thank you. I was quite intrigued by the whole chart where you were.
I like it, yeah.
I'm just wondering,
one more question. So Everett asks, what is the distinction between postdocs and fellowships? Is the latter a subset of the former? Do fellowships lead to tenure track positions at the same institution?
Okay.
And then, sorry, it's followed by a comment, because I think that
Yep.
it was mentioned that fellowships can be 5 years. This sounds semi-permanent to me.
Okay. So yeah, the first question, so the distinction between postdocs and fellowships is that, I mean, there are descriptions where you can call it a postdoc fellowship, for example, just to muddy the waters further. But generally we mean by a postdoc position, we mean a job that is advertised by an academic to work on their work. So it's, you know, you're responding to a job advert essentially. Whereas a fellowship is something that's personal to you, so you're doing your own work, you've been funded to do that work because you've applied for some money from some government or charity funder. So you've done that in your own right and you choose where you're to be hosted. So if you like Nottingham, then you come talk to us about being hosted here, fabulous. If you don't like Nottingham, then you go off and talk to some other institutions. So the distinction is postdoc is doing someone else's work, fellowship is doing your own work, basically. The other question's about whether it links to tenure track. So most no is the short answer, with the exception of the Nottingham Fellowship Scheme, because that's specifically designed to lead to tenure track position. And there are some similar ones at other institutions in the UK. What I would say, though, is that if you do win a senior fellowship, by which I mean one that is one where you normally only apply where you've already got 2 or 3 years experience post-PhD under your belt, so it's typically a 5-year fellowship and it's funded at the higher level of salary, as I mentioned earlier. Then quite often if you do win one of those, when you're applying to an institution or department to be hosted there, one of the things they will consider is, are you a suitable potential permanent employee? Because when you are appointed at that level, essentially the main consideration is that you'll become returnable to the Research Excellence Framework, which is the every 7 years assessment of UK research. So I have to kind of take those considerations as if they were recruiting a new academic member of staff. So therefore, you're kind of considered as a potential permanent person. There's no guarantee, of course, because if you do a terrible job in your fellowship while you're with them, they're not going to keep you on. but if you do a good job with it, there's a pretty good chance that it will lead into tenure track. So that's the long answer. Has that covered all of it, I think?
And I think that is all of our questions so far. So I would like to extend the thanks to David once more.
Okay, thank you. Okay.
So this brings our first half of RQI Nottingham to a close. So we'll take around a 25-minute break now and resume, or maybe half an hour break, so resume about 3:05 UK local time, or half an hour from wherever it is you are now. But before that, I'd like us to thank all of our speakers once more. Thank you.
Hello, everybody. Welcome back to the second session of the RQI Nottingham conference. Speaking now is Silke Weinfurtner, and she'll be speaking about classical and quantum field theory simulators based on normal and quantum liquids. Everybody give a round of applause to Silke.
You have to put this like this. Okay. It's a bit of a... First, thank you for the invitation. It's also a bit of a bizarre talk to give, because I'm going to has a bit of a sales pitch to people that are already here. So hopefully that motivates you to stay. Right. So I've been asked, and I should say that it is not really scientific saying. It's about like what are the main objectives here, a little bit scientific, but also what we're doing, who is involved, how is it to be to come and join my team here in Nottingham, and to explain a bit how we do things here. And the first thing is, if someone asks me why I like it here, what is the biggest bonus being in Nottingham? And then the first thing I would say is because of the colleagues, because of the people. So I call this team Nottingham, and so there's a bunch of us. Some people are new. But what this slide really shows, and I think this is rather remarkable, is not that I have such a big group. This is by far not true. But it's, let me start with perhaps older people here, is a bunch of colleagues. And that's what makes it special. That allows us to really combine theory and experiment here in Nottingham, where there are a bunch of us experimentalists. That is Tony Kent, Richard Hill, and myself. And then we partnered up with calculational powerhouses such as Jorma here, Tassos. And then it's not all of it. So we have, Jorma is in the School of Mathematical Sciences, so am I, surprisingly. Tassos is from physics. Tassos is a cosmologist doing theory. Jorma is, I guess, expert, I would say, gravity and quantum field theory. Tony is doing quantum optics experiments. Richard is doing strong gradient magnetic fields experiments. And now comes the part which I'm very proud of. It doesn't stop there. We also work with Lina Janssen. We have a joint grant, and she's from philosophy. It's fantastic to work with her. Then we have Ulrike Kuchner. She has a degree in art and science. She's an astronomer and an artist. And then recently also, as part with the grant with Lina, we're also working with Marco, and he is in mathematics, and he works on what's called the inverse problem. And what is also wonderful is that with, not all of them, but with the first three people here, I'm sharing joint PhD students. And that, I think, is a wonderful experience for PhD students here, because they have double the advice they can get, double their expertise. And in particular, I shown here the team, but that's actually some of the students are not really my students, I would say. Perhaps I'm somehow a second supervisor, but sometimes even not that. They are Jorma students, but what I really like about this is that our students just merge groups. And they did this without us asking us, so that means they really wanted it, and I think that's wonderful. So that's us here in Nottingham, but we are also part of the UK, and something that I think is a wonderful opportunity for people working in this group, because they also become part of a wider network that's called Quantum Simulators for Fundamental Physics. Tony, Jorma, and myself are on this. So if you look at that, who is part of that 7 research organization is sort of nicely, from a political viewpoint, sprinkled out throughout the UK. And so how many people are involved, and what are we doing? So first, the scientific goals. So quantum simulators we want to build a network of quantum simulators for black hole and early universe processes. The community is 50-50 quantum technology and fundamental physics researchers. We have 27 people funded through this network grant, but we also have 48 partners, and not just within the UK, but also abroad. There's a governance of 3 people that have to do all the unpleasant stuff, and I'm part of that. The experimental facilities, as I said, it's SEER and experiment combined. So the fundamental physicists, they provide high-level modeling for our experimental systems, and those are placed at, first one is St Andrews, Nottingham, Cambridge, and Royal Holloway, London. Okay, so, and I think this is a wonderful opportunity because it shows that this is a timely area of research. It shows that there is a big interest within the country, many connections people can make. So I think it's a wonderful place to be, and I wouldn't be aware of any other country in the world that would support this line of research as much as the UK is currently doing it. So we're very thankful for this support, but we're also working very hard. So this started in 2021, and what has come out of it, 1 patent application still pending, 25 publications, 6 preprints, 4 feature news articles, and 4 wonderful quantum simulators. Okay, so what are we interested? What's the physics? Beyond going down to a particular system, and what does it mean? So how does this all come together? This fundamental physics and quantum technology. So perhaps what I should say is what we are primarily interested in is quantum field theory. And quantum field theory, or any field theory, can become interesting when something is happening. And there can be 2 basic classifications you can make. And the one is that you say, well, the fields are what we call non-interacting, or the fields are interacting. So for interacting fields, you can have scattering processes. For non-interacting fields, you don't have scattering processes, but you can have conversion processes. You can have other things happening. But of course, if there's just a non-interacting field, this could be a bit boring. So you have to add something interesting. And so what you can do is you can stick this non-interacting field on a curved space-time geometry around a black hole in the early universe. Or you can ask about these field theories, which we are interested in. I should say that these are relativistic field theories. You can ask about the measurement process. As Jorma showed and explained, and we had other talks about, does everybody agree on the presence or absence of particles? And how do you measure quantum or relativistic quantum field theories? So, but then of course also then you say, well, interacting fields can be really interesting, so can go through highly non-equilibrium processes. They can scatter, you can have scattering processes, as Silvia mentioned already and Sean, as part of this preheating scenario. But you can also ask yourself, well, what if I have a field theory and that's metastable and it can decay and undergo phase transition? It's a wonderful, interesting, and hard problem when we are looking at quantum fields undergoing, for example, first and second order phase transitions. Okay, so I have a few slides where I go very quickly through the motivation for me to start working on this field is linked to Bill Andrews' seminal paper in 1980, where he realized that looking at sound waves in fluid flows, that you can have 2 different situations. So you have, suppose you put a little speaker into the fluid flow, and you look how sound propagates through your medium, your liquid. And then he realized, well, if I add the speaker where the flow is subsonic, so the flow speed is slower than the sound waves in the system, they can go in both ways. However, the situation changes very much if you were to put the little speaker downstream of a waterfall, and let's assume the waterfall is increasing in velocity, and I can define an area such that everywhere in this area, the background flow equals the sound speed at that point. And so all the sound waves will get dragged downstream. Sorry, I was looking for that word. And so that gave him the idea that perhaps you can set up acoustic horizons in this system. And then he went back, he gave a lecture in fluid dynamics when this came about, and then he did the math and he found actually it's not just a conceptual analogy, it's really strong, it's a mathematical analogy. And as Jorma said, if the equations are the same, the physics should be the same. And in particular, he managed to write for small fluctuations, so you use perturbation theory. He wrote this in these very compact way. And I will talk about in a bit what this psi field is really, but he has this really compact wave equation, and here there is this GAB, which we identify as a metric tensor, and this metric tensor here is provided by the background flow. So it's perturbation moving relative to this medium. And this equation, and I can be very fast because you all know that, this equation comes about when we try to write down fields, classical and quantum fields, and we write down, for example, start with a simple and ad hoc extension for the people who are not familiar perhaps with quantum field theory in curved spacetimes or analog gravity. You can ask a question, so if I look at the wave equation for some scalar field, I can write it in this very compact way, introducing a Minkowski spacetime geometry. And so this is just a rewriting in a way, but it gives you an advantage, because once you have the equation in this form, you can say, what if my scalar field is not residing on a flat spacetime geometry? What if it is residing on a curved spacetime geometry? And what you can do is an ad hoc or minimal extension of this by simply replacing your flat spacetime geometry with a curved spacetime geometry. And this is a very reasonable extension. It's not the only way, perhaps, to write down a scalar field on a curved spacetime geometry, but it is the most simple, so the simplest approach to translate field dynamics from a flat to a curved spacetime geometry. And this is what in quantum field theory in curved spacetime, in classical field theory in curved spacetime, what people use mostly as a starting point. And this is exactly the equation that Bill found looking at these fluid systems and sound waves propagating in fluids. And so here's the analogy, and then, okay, you say, well, it is a neat analogy. It seems rather bizarre that this part of mathematics drops out of these systems. What I think is also really nice is that in the analogs, you can derive this set of equations, while when it comes to field theory in curved spacetimes, you have to ad hoc write it down. So now, nevertheless, it's a simple equation. Here we are still considering non-interacting fields, just how fields residing on a general curved spacetime geometry. But the thing is with classical and quantum field theory in curved spacetimes is that it really matters. And when does a theory matter? And to me, as an experimentalist, when something matters is if it has some prediction, if something is happening, if there's an interesting physical consequence or process. And I think that is also distinguishing, in my opinion, quantum field theory in curved spacetime from many quantum gravity candidates where they're wonderfully in a sense of a fundamental approach, but where there's very little observable consequences or physical consequences. So I think in this sense, quantum field theory in curved spacetime is a wonderfully interesting theory. And if you go through this, and we have talked already about this to some extent, to some of them, there are wonderfully interesting physical processes and consequences coming out of this, I would say, almost rather simple extension from flat to curved spacetimes. So the most prominent one is the one discovered first by Stephen Hawking, where he looked at how quantum fields behave around a black hole, and he realized that the black hole, although classically absorbs everything through a quantum process, it can radiate away its mass, and that's stopped as the Hawking radiation. A classical process, but also has a quantum equivalent, is, well, what if I have a rotating black hole? Can the rotating black hole interact with its environment and sort of radiate off its angular momentum? And yes, there is this process that's called superradiance when you work with waves, and it's called Penrose superradiance when you work with massive particles, massive objects around. But also, sometimes, although quantum physics is not usually the dominating force, if you go back to the very early universe, it's dominated by quantum. We believe it is dominated by quantum physics, by quantum fluctuations. There was nothing else to begin with. And the question is, how can we turn from nothing from these quantum fluctuations, get to everything that we observe today? And so, again, you use quantum field theory, and there's a process that would allow us to consider, for example, the large-scale structure would be the seeding process for the large-scale structure, and its origin would be in this quantum field theory framework. And the other thing you've heard already a lot about it, because Jorma is one of the leading experts on this, is related to the Andrew effect and the fact that an accelerated observer and an inertial observer, they disagree on the presence or absence of particles. So this is the measurement problem within relativistic quantum field theory. And that's, to me, it's one of the most fundamental processes you can think about it. Is something there or not? How much more basic can it be? So super interesting. Now, I said quantum field theory in curved spacetime is superior in some way because it predicts all of these wonderful effects. But there's a problem. And it's a problem perhaps not many theorists are so much concerned about, but as an experimentalist, it almost nullifies all these wonderful effects that should come out of the theory. And the problem is beautiful theoretical effects predicted, however, no experiment, no observation. And this is, for me, that was the motivation to turn to something different, what's called analog gravity, and the idea to set up these effects into a controlled laboratory environment. And in particular, there's a broad class of system where this analog gravity, which can facilitate an analog gravity experiment. And that means that small perturbations are, to some extent, governed by this simple equation for scalar fields and curved spacetimes. But I'm personally mostly interested in liquids. And I'm interested in normal and quantum liquids because I also find it always extremely interesting and important to compare what more do you get when you actually use a quantum system compared to a classical system or a normal liquid in this case. And what I'm interested in is interfaces that form. So it could be between two liquids or a gas liquid, but in general I'm interested in two-dimensional slices on classical and quantum liquids. And this is what we are mainly focusing on in Nottingham here from an experimental point of view. Okay, so, and I want to put this a bit in context, but I should be fast because I want to tell you also a bit more of what we're doing here. But so the idea is we have this set of equations, it's very universal, comes out of many systems. And one of the things which I also wanted to talk about is what is this psi field here? And this psi field here is actually in fluids. You have density and velocity perturbations. And what this psi field is, if you take a fluid and you assume the fluid to be irrotational, you can write the velocity field as a gradient of a scalar field, and that perturbations in this scalar is where you get this equation out. So if you see something like that, perhaps it's not the best analog. But what I wanted to show, what I wanted to make clear here is these are not the density, these are the velocity perturbations in the system. The relation between the two is similar as fields and conjugate momentums, and this takes the role here with phase and density fluctuations or interface fluctuation, depending what your medium is. So it all started in '81 with Bill Unruh, and what he started with initially is the Navier-Stokes equation, and then basically he took the Navier-Stokes equation and he did what every theorist does. He threw everything away that's nasty. So he worked with an ideal fluid at the end, irrotational, inviscid, whatnot. So the dream system for analytics. And that's how he derived his equation. There is a candidate that, of course, is very close to an ideal fluid, or which is Bose-Einstein condensate. And in fact, if you look at Bill's derivation, one could argue he really derived it for a BSE because he's thrown everything else away. And these systems are ideal fluids, superfluids, these Bose-Einstein condensates. And again, people are looking at sound waves and propagation within, and then they showed that you can write it in this form. Okay, so the stepping stone from this to the other thing was that initially this was all classical systems, while this one here, the bottom one here, is really then a quantum system with quantized sound waves. Now, the situation I'm interested in if you were to ask me what's the mass, I would say, well, one Navier-Stokes is not enough. You take a set of coupled Navier-Stokes. So you have two liquids or gas-liquid, and what you get is this interface. So if you have immiscible fluids that don't mix. So both gases and liquids are fluids, but here I have something that separates them, and this interface is what I'm interested in, the dynamics that happens on this interface. And the first ones to do this was Ralph Schützel and Bill Unruh in 2002. They showed that these interface waves can be ideal simulators, and that is related to the tunability of their propagation speed. So this was in classical fluids. And so the stepping stone then is also that there is a quantum version of this. So the most natural extension from a classical fluid to a superfluid would be superfluid helium. And superfluid helium, unlike Bose-Einstein condensates, they can also form interfaces because they are liquids. This is a gas and this is a liquid. And liquids are harder to deal with. In my opinion, more interesting. They have a more complicated or more complex effective field theories. They have different regimes. They have interfaces. So I'm quite fascinated simply by these complicated systems, complicated and wonderful systems that they are. So, and when you want a simulator, it's the same as a numerical simulator. You want to have many knobs to explore the parameter space and set up many interesting systems. So already if you take more fluids, you can set up more interesting physics. And so that's also already that if you have an interface, you need two fluids to actually set up an interface, and that also gives you additional tunability. And this is generally true. The more knobs, the more interesting your simulator is. And if you allow me to use any system, not one specific, but I say, what can I do if I use the full potential of these analog gravity systems? You can set up these space-time geometries, flat space-time geometries in homogeneous or static fluids. You can set up black hole horizon in stationary flows. You can have cosmological scenarios in time-dependent if your propagation speed is time-dependent, for example. And Sean and Silvia have been talking about this. Okay, you can even change the signature of your emergent space-time geometry, because what you have here in this GAB, this G0, the sign of that determines the signature. If it has the same sign as the spatial components here, where they're all positive on the spatial slice, then it's an Euclidean signature. But if you have the G0 sign different, then we talk about this Lorentzian geometry. So you can tune a system from where you have hyperbolic equations, propagating modes, to elliptic equations, exponentially growing and damping modes. Now, that's not all, because as I said before, these are interacting fields. And so when we talk about sound waves, we usually throw all the interactions between the modes away. And of course, this is sometimes a good approximation, but if someone asks, what is the full effective field theory? And then it looks like that. So you have a kinetic term, you can set up a mass term. That mass term can be stable when m squared is larger than 0, so a nice mass term if we think of it. It can be an imaginary mass, and it can be unstable, and you can make it metastable and you get the false vacuum decay. So super cool, this term. Then you can say, let me stick something in, let me interact with it locally, let me put in a particle detector. I can couple to the field and to the conjugate momentum of the field, super cool. And then I can say, well, how do the modes actually scatter with each other? And then you get all these combinations of between the density and the conjugate momentum, and how you stick them in, you get all these interacting terms. So it's wonderful, but you have to, of course, look at each system individually, but this is what you can do with them. That's sort of the totality, and some terms in some systems might not be there, and you can make them negligible, but this is what the theory gives you to work with, or the system to work with. Okay, so here we are. They have super nice effective field theories. They are provided by these fluids, could be superfluids or fluids, and the field theory is super exciting. And so what I'm interested in is to understand and really probe this effective field theory to an unprecedented level, so that we really know these are the equations. And this is really not a trivial question, particular systems we're looking at. And want to develop methods and toolboxes for these fluids to actually extract this information. And there we use some of field theory methods from particle physics, cosmology, to actually study these field theories. Super cool, get very deep insights. Now, when it comes to quantum field theory in curved spacetime, at sort of the zeroth level in all these analogs, you could say, well, there's all these wonderful ideas and I want to turn them into reality. I want to have a system that undergoes Hawking radiation because I can't see from a real black hole, and I just also want to understand what are the conditions, the environmental conditions for this to happen. But also starting an experimental area, you're training a whole generation of people that have both. They have very deep theoretical insights, but they also get a feeling what it means to do experiments, right? So you're basically saying, look, it's not just theory, it is experiments, not perhaps for what the systems for which this book has been written, but this book has been written for a lot of systems. Okay, so that's where I feel, well, in order to do that, you need to set up field theory simulators, and that's what we're doing here. And of course, the goal is that you simulate something that you can't calculate, that you first say, I make it work, and then I push myself into a space where the theories perhaps struggle to see if I can get some inspiration for something more and explore the parameter space. So this is why we built these field theory simulators, to put these two things together, right? And then, of course, what is the driving force here? Well, it is quantum technology, and in particular, to set up these quantum simulators, what we are using superfluid helium systems, and also we need to then interact with this system using quantum sensing eventually, but we're slowly working towards this. Okay. So the simulators in Nottingham is a bit like the Christmas carols, the ghost from the past, the ghost from the present, and yet to come. So the ghost from the past is where our normal fluid interfaces. This is how we started setting up these black hole simulators, these rotating vortex flows. And we're looking at interface waves interacting with this vortex, a big vortex that forms in the center. Or Silvia and Sean's talk about two liquids that don't mix. And what we're driving is parametric resonances in this system and compare how mode scattering occurs. So this is not quite the past. We're still working specifically on this one. But what we are doing, or have already started, we are translating all of this to helium. And this is an old picture of the setup. It looks much more involved. And Pietro and Leonardo will talk about this as well. So we go to quantum fluid interfaces, or quantum liquid, it should be written here. And then at the end of this month, we will get a new machine. We get a proper fridge. And with this one, we can go down from here around 1.8 Kelvin to 300 millikelvin. So we get colder and more quantum, because eventually also we really want to deal with fragile quantum states. And, right. So, right, I have to probably, how much time do I have left? Okay. So another reason why helium, so when it comes to quantum simulators, everybody would say the system to choose is ultra-cold atom systems. These are the systems which has been super successful. So why do we need another system, and especially another one that we have, we already know for so many years? So why is it now? What has changed? Why should we go back and study superfluid helium at these levels which I'm proposing here? And I wanted to, sorry, and now I'm field theory. Yeah. I wanted to go to some other slides first, so that's a bit of a pity. I'll come back to this, why superfluid helium, why is it so interesting, and what we know or don't know theoretically. And I think whenever you don't know something well theoretically, then experiments really make a lot of sense. And I will come back to this thought. Apologies. So what we have done first is we set up these vortex flows. And in particular, why am I interested in any sort of vortex flows where you have a gigantic vortex, let's say, in the center of your system? And that is because these things are called bathtub vortex flow. These are stationary draining fluid flows. And they are interesting because they have super cool flow behavior. And in particular, this one here, this is not working, maybe this is working, yeah. So if you drain as a rotating fluid and it drains through the center, so it has an angular momentum and a radial component. And if you ask yourself, so how does a system like that actually drain? What is the resulting flow field from this? And what is super interesting is that most of basically in the bulk, what's called the bulk part of that flow, there's almost zero draining. All the draining happens through the boundary layers on the top and the boundary layers on the bottom. Now, because they can't really just cross each other, so what is happening on the bottom here, it's called this Ekman pumping. So when you come close to the center, instead of draining right away, you have an upwelling. It goes up, turns around, merges the thing from the top going down, and drains. So this is already, you can see, very easily set this up in a classical system at home. And this is a wonderfully complicated flow behavior. Now, one thing in superfluids that's not so well understood is boundary layer flows. So already here there are things that are, perhaps classically can be understood well. From a quantum perspective, they're quite challenging. Now, the first system that we set up was this big, so the warping comes from taking the picture, but this is sort of 3 meters long, 1.50 meters wide, and the basin height is half a meter. So we have a drain in the center, and we get the angular momentum by inserting the fluid flow in a way that you give the flow angular momentum. So we set up this giant vortices here, a bathtub vortex in the center of the setup. What's a bit unusual is that usually when you were looking at vortex flows, you would rotate the whole setup. And this was a deliberate choice not to do it, and we did some tests that this would be all right. And what we did initially then, we studied how interface waves would interact with this vortex flow. And so more recently what we did is to simply translate this to superfluid helium, and you will hear much more about this, so I can just browse over this and refer to Pietro's and Leonardo's talk. Okay, what you can do, why is it interesting? So why is it interesting for curved space-times? Well, rotating black hole configurations or rotating curved space-times, they exhibit a plethora of physical effects that are really important, such as, for example, the black hole superradiance. And this is what we built the big tank for, and this is the first experiment we did. Then by looking at the system, we realized that the vortex flow itself doesn't seem to be quite so quiet. It seems to give off some noise, which one could see by eye, and eventually we figured out that these are the black hole ring-down modes that you can extract from this system. So this was the second experiment we did. Okay, we did more experiments, but I don't want to get into it. So it seemed just like from these classical experiments, it just seemed to work really well. All these processes that we expected to occur around black holes, they seem to also occur in this vortex flow. And in particular then, and again, I should browse over this. So one of the first challenges we had was to set up a vortex flow in superfluid helium. And this is what Patrick has been working on relentlessly over the last 2 years now with Pietro and Leonardo, and wonderful work has come out of this, and you will hear more about that. And it's just sort of, this is one of the few quantum vortex flow of this kind, stationary draining vortex flow in the world. There's one group in Japan who has, let's say, a similar setup. What is unique about it is also that it's fully transparent, because we use magnetic coupling to drive a little rotor inside that cryostat to recirculate the fluid. Okay, so why is this interesting? Because here we have a system that can set up, and as we've shown, the biggest quantum vortex flows ever achieved. And you can explore how a vortex flow, which usually consists of quantized vortices, and I'm sure you will talk about that, how this can become classical. The open questions, there's so many open questions, how exactly this vortex dynamics, how vortex lines arrange themselves in such a system, the wave-vortex interactions on that interface. That's what we want to study. And we want to derive sort of modeling support for that. And this is a really hard system. So as it is here, the full dynamics of this, I wouldn't know how one can simulate that. Thank you. OK. And then there, of course, from the curved space-time geometry perspective, there are many applications. Super interesting system. Now, why helium? And I have to just go through this. This is something from Carlo Barengi's talk. There is no one theory for superfluid helium. And that is wonderful. So in fact, you can put yourself in a situation where you don't have a good theoretical model for the dynamics of the system. If you don't have that, how do you do perturbation theory? How does it all work? And in particular, there is this distinction between irrotational and rotational. If it's irrotational, we use this Landau's two-fluid equation where you say I have a two-component flow, which is mixed, and there's a normal and a superfluid component, and depending on how cold or warm you are in this helium-2 phase, you have either 50-50 of it, you can have almost only normal component, or it's if you're below a Kelvin, you have almost everything is superfluid component. The problem is, how do you add vortices to it? Okay? So for this, if it's really cold, there's some modeling assuming that you can use the Gross-Pitayevsky equation. It doesn't really work so well, and it doesn't have an extension. You can't just extend this when you also have a normal component. The Gross-Pitayevsky will give you an ideal fluid, not the Navier-Stokes equation. And then there are different ways, depending on what vortex modeling you want to do, there are different models. I'm not going into it because I'm running out of time. But clearly, from a theoretical point of view, this is very unsatisfying. But it's also perhaps a nice challenge to use experimentation to pinpoint down which models actually are applicable and give you the best match to experiment. Perhaps you can even go a bit further and give some insights for theorists, and Carlo Barengi is working with us closely to perhaps make this a bit more sensible, this whole picture. Right, non-equilibrium field theory simulations. Silvia said that already, I'm running out of time, and Sean, so here really, these experiments, and just to say what motivated me to look into this, I wanted to understand how well can I measure an interface, and how well can I understand the effective field theory? Because what's happening on the interface is you have two liquids that mix. And sort of from a chemical process, the one is going into the other and vice versa. So it's a sort of a chemical balance where you form an interface. But the interface has a thickness. And so one of the questions I wanted to understand is, does this interface make sense below the scale of that thickness of the interface, that you have a well-defined interface from an effective field theory point of view? And the answer is yes. And then also what I wanted to understand is, when does it become linear and nonlinear? When is the transition? Because usually we always say when the amplitudes are small, it's linear, but what does this mean? And at which point can I not neglect my mode scattering in the system? So this really was a test. This was the first test, and for me, this is a defining test that liquids are good quantum field theory simulators. Okay. Now, I shouldn't go into it too much because it has been talked about. It's just that I thought it was really nice. So this is a snapshot taken from Feynman's last Blackboard. There are some big statements on here. But he also said there are things he wanted to learn at the end of his life, things he hasn't quite understood, and accelerated temperature is one of the effects that he had on his Blackboard as something he wanted to understand in more depth and work on it. I'm browsing through it. Thankfully, Cisco did give a talk about this, and what I'm interested in here is, in particular, Jorma motivated me to get interested because I was evaluating all of his, or being an examiner, internal examiner for all of his students. And two things, whenever I asked them, how would you build this, they would just completely break apart in the exam. But also, there was this, I use this coupling or that coupling, and it shouldn't matter. And there was this sort of, everything is allowed. And that bugged me a lot. And I said, well, let's go down and let's build a detector. And then none of this is possible. You have one way of modeling this. And I sort of say, look, can you make it work? So I was particularly interested. I want to build a particle detector with Jorma together and with Cisco and all the other people and Cameron here. But that sort of was the motivation for me. It was too much theory, too much freedom. Jorma had too much of a good time, I felt. So, right, and that brings us to the last parts. I really need to run through it. So, how do we interact with it? And so usually there was always like, people would go through extremely great lengths, like Jeff, who set up this wonderful, black hole horizons in 1+1 in one-dimensional BSEs, and saw all these nice effects. And most of the effect was really on setting up the background flow. And when you looked at the detection methods, they were sort of like, they were high-end, super high-end, high-class, but they were always sort of the conventional ones. So there were two issues here. There were no conventional ones for liquids, so for the interfaces, but also, for example, the Andrew effect is it's a measurement, and it's a local measurement, and you don't immediately destroy your whole quantum field theory. So clearly, the whole measurement, you need to treat it equally, take it equally serious as setting up the background flow. So what we needed to do, we needed to opt up our game, and the way we do it is we use interferometric techniques. And so this is a picture of our new cryostat. Will come end of the month. We have nothing to put it on, of course, because something unusual happened. They said we would get it next year, early next year in January. So I was expecting it in March, but we're getting it earlier. So it's the first time that happened to me. But so with this, we can go down to 300 millikelvin, and we will be working with thin-film helium systems. And we will set up global detection methods, which Vitor will tell you all about. And we will try, and this is the hard one, to set up local detectors and to either see what's left behind, as Adam said, there's something you left behind, or perhaps, if we can get it going, extracted signal also from our detector directly. What is a detector is a completely different question. The laser beam is not the detector. It's part of the detection scheme. Right, so this is what Vitor will be talking about. And the scientific summary, and then I need to get another 3 minutes, hopefully. So the primary objectives really are to establish quantum liquids as a groundbreaking finite temperature non-equilibrium quantum field theory simulators. Big words. This is not to replace or saying that this is better than ultra-cold atom system, because that would simply not be right. They are different, but they have something to offer, something interesting. They can have the capacity to accommodate substantially larger system sizes. And this is something Pietro and Leonardo will show that this actually can give you an advantage. They have inherently strong interactions because they're liquids, not gases. Interacting quantum field theories are hard and interesting. So that's what you want to do. They're hard problems. You can actually fix the temperature. You can have a quantum field theory at finite controllable temperature, and you can have the system for 50 hours in that state. It's something the BSE people can't do. To really have a finite temperature and set that and regulate it. And you have, depending on where you are, of course, if you're in the super fragile, 1 millikelvin regime, there's no hope in there, perhaps then you have to worry again. But in the regimes we are looking at, they are non-destructive spatial and temporal analysis. So we have unequal time and unequal space. We can reconstruct everything from our measurements. Okay, so that's why I work on this. And now I get the last 5 minutes to just say a bit about going beyond the science. So if you come to Nottingham, one of the things I'm very proud of is what else we are doing. And the first thing we are doing, we do little events like we try to inspire the next generation. And Leonardo put a wonderful picture together, video, and that only works if I go out. So we did this special event. think I have to stop for the time, but because we're running short of time. But every time I see that video, it makes me tremendously happy. So this is one thing we're doing. We're also commissioning artwork, working with artists. So we formed an art lab that sort of, I think, was originated in our group together with Ulrike Kuchner. And we did sort of the first events of this, get some started and motivate colleagues to follow. The first artist in residence we had in the art lab, in the room you saw where all the kids were drawing and being creative. That was Konrad Shokras, an extraordinary artist, extremely inspiring to talk to him. And he will design for us an artwork that will be in our art science exhibition to take place at the beginning of 2025 for 3 months on the Arts Gallery on campus. It's a collaboration with Lakeside Arts. And what he symbolizes here is a black hole ring down using 2 bronze bells that move through this mesh where there are magnets on the antenna. The antenna represent the space-time fabric, and the bells, the black holes, and how they send gravitational wave through the universe. So this is one thing we're doing. We're working with artists as well. We have, and then I'm stopping very quickly then. The art lab itself, we also do things here. So Patrick spent a lot of time of putting this nice Lego interferometer kit together, which then is a working interferometer, which we're building for kids to come and to train. And so that's also part of it. We want the kids to build their own gravitational wave interferometer here. We work on impact together. We develop sensors here. This is a sensor which we exhibited yesterday on the National Quantum Technology Showcase. We have 2 pending patent applications in the group, one for quite a long time. So I have a slide why the UK. There has been, and it is a bit of an issue, Brexit didn't make us the most popular country in Europe. But you know, when it comes to this field or quantum sciences, the UK is absolutely committed. Just recently put 2.5 billion into quantum sciences and fundamental physics, and the overarching program that also funds this quantum simulators for fundamental physics network that is also be funded through this. And as it looks like, it will be further supported beyond the first phase of the funding. So the UK is a great place because we're using quantum technology for fundamental physics more generally, and there are 7 large grants, and quantum simulators for fundamental physics is one of them. But they're also building detectors for dark matter, for axion fields, for many wonderful, wonderful different things. If you look at the QR code, you can look up all the wonderful science. And that leaves me with the last slide, and I tried to avoid looking at Cameron, but as Jorma said already, join us. We're always looking for students, motivated, good students that like to interact and be in such a, let's say, perhaps a bit unusual, but a very open environment. So thank you.
Thank you very much, Silke, for the talk. Are there any questions from the room? Any questions online?
Anyone second thoughts now?
I have a question, Silke. So you mentioned before that the philosophy is if 2 systems obey the same equation and the physics is the same. How much can you say about the more fundamental structure of each system? Can you learn about the gravitational system from the condensed matter system?
So, I mean, this is, to be honest, partially also why Lena basically suggested, she was working in the lab, and she did her master's in gravity, particle, and fields, and in her dissertation she ended up in our lab. And so she knows the math as well, which I think is really remarkable for a philosopher, and she did this while she was an associate professor here. So, and she did extremely well in the mark, so she's a very remarkable person. But then, of course, also how much can you learn about the target system and whatnot? There's this whole language about this, so this is one thing we want to discuss. For me, this a lot, I'm a bit more of a practical person. I'm thinking of anything that relates on something being exactly right, any process that when you deviate a little bit, because nature is not this way, that there is only one effect happening and all the other physics is just not there. So this robustness and universality and how you learn how to extract the information from these systems and what it means ultimately forces you to understand these effects beyond what perhaps you could come up when you have a piece of paper and a pen, working things out. So there are things like how much further can it go? So can you use this system if you set them up well to perhaps go in a parameter space to learn something you couldn't calculate, use it really as a simulator. For back reaction processes, well, you can also simulate that, but through a quantum system, it's not so clear how this works. You could, like the false vacuum decay, that's a really hard case. Could you see some signatures coming out which we haven't predicted? Could we find new effects? And then you would need to check if really in the gravitational side or in the, this is still there. So you cannot just say, I found something in the analogs, it should also be in the other. But also the depth of this analogy needs to also be investigated further. So it's a hard question, been asked many times, mostly in grant when it comes to grant applications and reviews and papers and referee reports and interviews. It's a wonderful question, and Lina is going to answer this in the next year. That's all I can say. Me too.
Okay, if there aren't any more questions, then thanks, Silke, once again.
To change this, right? Cameron, how do we do it? Display mute, and then PC. And then, yeah. Okay, and now I'd like to welcome Leonardo Solidoro to the stage to talk about QFT simulators and superfluid helium vortex flows.
So, hi everyone, thanks for having me. So yeah, basically this is the first presentation where we present our experiment when we try to simulate QFT anchored space-time using draining vortex in superfluid helium, helium-4. Yeah. So in particular, I will focus more or less on the theory background that Silke more introduced, and on how we can characterize and detect such surface wave propagating on top of our system, such that we can study this analog gravity effect. So, as Silke introduced, the idea of analog gravity is that we can map the dynamics of perturbation propagated on top of continuous system to the dynamics of fields on curved space-time. And there are many systems where exhibit this kind of behavior. For example, the original UNRO paper proposed this perturbation to be sound waves, so pressure and density perturbation. But the same thing happens when gravity surface waves are concerned. So the model that we study is basically modeled as a fluid propagating between a basin and a free surface in the shallow limits. So in the hypothesis that the length scale defining the heights of the field is much lower than the typical length scale of the waves. Particular, the physical system we consider is made of an inviscid fluid flowing irrotationally. So inviscid fluid means the governing equation are basically the Euler's equation, and irrotational means we can introduce this scalar field quantity called the velocity potential, from which we can retrieve the velocity. So by perturbing the equation of first order, we get this couple of equations for the perturbation of the velocity potential and the height field, which can be recast as an effective Klein-Gordon equation for these perturbations, whose metric is given in terms of the velocity flow of the field, and it depends on the speed, on propagation speed of the perturbations, which can vary as the basin changes. So this is basically the idea behind it. but we focus on a particular class of flows, vortex flows, that in general have this form. This is the general form of a rotational flow satisfying all this equation in azimuthal symmetry, so in cylindrical coordinates, where this is the radial coordinate, this is the angle, and D and C are two constants. So following this description in terms of the metric, we have an effective space-time whose line elements reads in this way. But despite the technicality, we can identify two regions and surfaces which are relevant for our analogy with black holes and gravity. Particularly, we can identify an horizon that is defined as the surface within which the velocity of the fluid exceeds the propagation speed of the perturbations. And this way, this perturbation cannot propagate outward, and so it creates an effective causally disconnected region, as in an event horizon for us for a black hole. And in particular, if this constant here, C, the circulation is not zero, we even can identify an ergo region, which is a region within the module of the velocity field exceeds the propagation speed of the waves and acts as an ergo region for a rotating black hole. In particular, this kind of flows, as Silke mentioned, has been established here in Nottigham in our big vortex, big bathtub in the lab, and they've proven that phenomena related to the presence of an ergo region, namely superradiance, for example, what as predicted in black hole physics, find their place even when surface waves propagating on water are concerned. But of course, finite viscosity prevents more subtle, more evasive phenomena to be detected. So this is why people moved to quantum fluids. So these fluids, quantum fluids are in general multi-particle systems where most of the components are in the same state. In particular, as an example of these are Bose-Einstein condensate, where most of the atoms composing the boson composing the system are in the ground state. Such coherence, phase coherence that emerges from this configuration allows us to describe the system in terms of a complex order parameters. And in turn, we can, remarkably, the dynamics of such system can be mapped to the dynamics of a inviscid flow by identifying the velocity with the gradient of the phase of these order parameters. And with this identification, we have that naturally such system have an irrotational flow, which is one of the hypotheses that we need for analog gravity to work in any simply connected region, of course. But circulation can still be present in such systems, but it can appear around some topological defects in the system, and remarkably, it is quantized. There is an integer multiple of a circulation quantum, where m is the mass of the boson composing the system. Among the different quantum fluids that one can consider, such as Bose-Einstein condensate or polariton fluids, we, as Silke mentioned, chose to work with superfluid helium-4. Remarkably, superfluid helium allows us to build a macroscopic system over which we have a full control of the characterization of the surface. And of course, our system can possess a free surface on which we can construct and study the analog theory. Superfluid helium is quite a peculiar quantum fluid because superfluid helium is liquid helium when below 2.17 Kelvin, when it undergoes this phase transition and acquires new features. In particular, it's a quantum fluid because it presents this kind of quantization of circulation. And remarkably, when you start steering it or introducing some circulation, you will see the emergence of such a topological defect as line defect propagated throughout the system, each of those carrying one quantum of circulation. even if in the as we approach 0 Kelvin, it becomes a perfect superfluid, but at finite temperatures, when we operate, it behaves or is phenomenologically described as a mixture of two fluids, a regular one, a viscous one, and an inviscous one. Still, even if the perturbation is, the viscosity is not completely zero, it's still a very low viscosity system when we can study our analog gravity. In particular, let me just mention a remarkable property, caveat when dealing with quantum fluids, because of course we have this macroscopic sample of helium and we steer it. We're introducing a macroscopic circulation which well exceeds considerably the dimension of a circulation quantum. So we expect such system, if used for gravity, analog gravity purpose, to present a larger number of circulation. Still, the circulation is quantized, so, but the problem is that a vortex containing more than one circulation, carrying more than one circulation quantum is an unstable state, and it rapidly decays in a bundle of singly quantized vortices. And this is quite unfortunate because they are their own dynamics, and they tend to repel each other and spread throughout the system. This is quite inconvenient for us because even if the surrounding flow is rotational, the spreading of these quantum vortices introduces or imprints solid body rotation to the system. So effectively, we can recognize the presence of such vortices as a solid body rotation which is imprinted in our flow. And this spoils the analogy with an effective space-time because irrotationality is required as an hypothesis. We managed to build a setup which consists of a stationary draining vortex. So when we confine such the bundle of vortices in the center outside the experimental zone, as Pietro will show you later. Now I will present to you how we detect the waves which propagate on our sample. So the idea behind we can detect with enough resolution both in space and time, and by sampling the whole surface of the fluid, is by exploiting this synthetic shielding imaging, which is based on the idea which every one of us maybe have experienced, that when we look at the fluid from above, with some known background below it, when where the surface is perturbed, is not just flat, these waves will produce an effective distortion of whatever is below it. And the idea is that if these waves are small enough, we can parameterize this distortion as an effective displacement which happens locally in this background below the waves. So if this is our background, as seen when the wave passes by, this is it can be parameterized as the background of the background without the waves, so the known background, but with the introduction of this displacement vector, which acts locally. So the idea is that we can obtain the information or reconstruct the surface by obtaining, getting numerically this displacement vector. For this, we use this technique called fast checkerboard demodulation, which exploits a two-dimensional periodic pattern. And the effect of this local displacement will be modulation in the phase on this known checkerboard pattern. And by analyzing it using this pattern, we can extrapolate the component of the displacement vector immediately. In particular, this is one of our a frame as of our experimental setup. So this is the pattern that we use. That is when the vortex is created. And you can imagine that on top of this, there is just superfluid helium, which is almost perfectly transparent. So what we do is that is recording an image of the imperturbed surface, so without any waves on it. And by fast Fourier transform, we can extract this carrier waves, which are the frequencies associated with the periodicity of our pattern. Then when the wave passes through, the FX is to modify locally the FFT or the spectrum of our images. So we can easily identify the peaks corresponding to the carrier waves and the effect of this perturbation with just to modulate nearby these peaks the spectrum of the image. So by identifying these two peaks and the modulation introduced by the displacement vector, we can just extract numerically the phases for each pixel as detected by our camera. And since we have two carrier waves because we have two perpendicular modulation, we have just a system of two equations for the two components of the displacement vector. So once we get the two components, we have this relation which gives us the gradient of the height field in terms of this displacement vector. This is just the distance between the surface and the pattern, and this is the ratio between the refractive index of the medium above the liquid and the liquid itself. So by integrating this formula, we are able to reconstruct the surface of our sample. This is an example. And this is more or less how we reconstruct the surface, and then we to facilitate the analysis that Pietro will present you. So of course this method has some pros and cons. The pros is that this is a very non-intrusive method. We don't need to introduce any external body to the sample because usually when liquid helium is concerned, some flow visualization technique involves the introduction of particles in the fluid which spoils the sample and can even affect considerably the flow itself. Then what's remarkable for us is that with this method we look only at the surface where our physics, our prediction of analog gravity are relevant. Unfortunately, there are a lot of parameters that enters in this with this technique. For example, the resolution of the camera versus the resolution of the pattern, all of these. So this makes kind of very hard to predict a priori the performances of our reconstruction technique, but we are working on it by performing some numerical simulations. And eventually, we want to reduce the circulation injected in our system and be able to resolve individual vortices. But this method is not well fit for it because it has a macrometric resolution. We can identify perturbation up to the micrometer scale. But fortunate enough, as Vitor will present you, we are moving toward a new technique called digital holography that will allow us to probe even this new regime. And yeah, that's it. Thank you.
Thank you very much, Leo. So are there any questions from the room? Quick.
So you said that this is a non-intrusive method because you don't have to introduce new particles, right? But at the same time, in order to see anything, of course, there are photons, there's light that goes through your sample, right? Now, wouldn't it be better to have a completely dark room and then trying to perform something like this by shooting very lasers of a very small frequency or something like this? Like, isn't the light that is going through the sample itself disturbing the sample?
This is the introducing laser is the next step. Actually, digital holography is concerned with dealing with lasers. I mean the thing that the light needed to perform this method affects is that it makes the helium boil. Essentially, the helium evaporates. So it's more concerned with the actual physics of the sample that we are looking for. But the fact is that in order to achieve the temperatures that we need, we use evaporative cooling, so we are losing helium anyway. And for the time being, this is good enough for us.
Patrick?
maybe I would like to just add a little comment to what was asked. I mean, in comparison to bosons and condensates, shining light through condensates will effectively, destroy your sample. Here, okay, we are introducing some light which can be actually absorbed by superfluid helium, but it is quite reasonable to assume that this intrusiveness is absolutely negligible to the drive, because we are driving the vortex mechanically. So actually the system is dominated by mechanical noise or by some pressure gradients that are driven mechanically. And as Leonardo correctly said, I mean, this is in these terms, and compared to what other groups are doing, this is minimally or basically non-intrusive method.
Okay, are there any other questions or comments online? Okay, with that then we'll thank Leonardo again. And so is it open, Cameron? Okay, and the next speaker is Pietro Smaniotto, and he will be speaking about superfluid helium vortex flow, a simulator for QFT and rotating curved spacetimes.
Thank you. Okay. Hi everyone, thank you for having me today. I will talk about the main results of a paper that together with Patrick, Leonardo, James from the University of Nottingham, and Silke, and also Sam and Ruth from the King's College in London, and Carlo from the University of Newcastle, we put together a paper about the results of our experimental setup in superfluid helium. And so this is how the setup looks like. You have already seen it from previous presentations. What I want to add is some technical details. So we have two sets of fully transparent glass dewars, concentric. The outer one contains liquid nitrogen that is here to do some pre-cooling and to shield the inner vessel that is filled with helium from radiation and other sources of heating. And so we cool down, we fill the inner dewar, the inner cryostat with the liquid helium, and then we cool it down to the superfluid transition. So our temperatures will be between 1.6 to 2 Kelvin. And what we do, as Leonardo said, we are going to reconstruct the surface waves with this checkerboard that we use as a method to reconstruct the height field. And then we do spectroscopy. So we look for what kind of frequencies we have. So we have a 2+1 system. We look at the surface. We have time, angle, and radius. So we look at the frequencies in these directions. Before going through the actual data analysis and results, I just want to give some technical details about the design, because it's not trivial to set up a vortex flow in a sealed cryostat at this low temperature. So what we have is an external motor at ambient temperature, which is equipped with magnets that are coupled to the magnets in the disk in number 1 in this plot. And then the disk is, when the motor spins, the coupling is also making the disk spinning, the internal disk spinning, which is spinning the propeller and is creating this vortex that is flowing down the hole and is going back up from going through a flow conditioner, which is this black cylindrical piece of plastic that really looks a simple thing, but is a bespoke 3D printed device that we, through a lot of iteration of the same experiment, designed to decouple the solid body rotation that comes from the propeller. We want to decouple the solid body rotation to the rotation that we want to give to the fluid at the surface, because as Silke and also Leonardo said before, we want a certain velocity profile on the surface. We want a potential velocity profile. I will going back to this later. And also we have the pattern that is, we need it for the checkerboard demodulation, and the experimental zone will be the surface. Okay, so this is a scheme on how we set up this flow. Propeller is spinning, is creating a cavity below the hull. Maybe I should use, below the hull, which is below the flow conditioner, which is this gray L-shaped thing in this scheme. And a cavity means that you also have flow from above, and you have recirculation because it's a sealed system, and recirculation through these small holes that we design in the flow conditioner. And with this system, we figure out that we can actually reproduce two regimes of a vortex. The first one, we call it solid core, and if you look carefully, there is no, it's just a dimple on the surface. It doesn't go all the way down the hole. So how do we explain this? We think that below this dimple, we have a cluster of singly quantized vortices that are, creating this dimple. While if we speed up the propeller, at some point you create a full cavity, a hollow core that goes all the way down the hole. And in this case, you don't have a cluster of singly quantized vortices. You have a single multiply quantized vortex, and this is the kind of quantum to classical transition Silke was talking about previously. Well, let's have a look at a video of the flow again, because you don't see this very often. And just to give you, some idea of the shape and how big is this vortex is. It's actually the biggest vortex with the biggest circulation ever measured. So it's very remarkable. Now, let's jump to the data analysis. So, as Leonardo said, we are reconstructing the surface. And when you reconstruct the surface, you get a signal like this, which is very confusing. So what you do usually, you just look at the modes that are populating your surface. So what you do, you pick a radius, so a fixed radius, wherever you want, and you look at the Fourier spectrum in the time and angle direction. So you look at azimuthal number versus frequency, and you notice that there are some frequencies that are populated, some frequencies are not populated. And in particular, you have these low M modes that are populating every frequency, and these are actually the cause of the weird colors in the previous animation I showed you. So if you filter these modes and you reproduce the animation, then you can see the interesting part. So we figured out in this way that all this vertical line is just mechanical noise due to the shaking of the propeller or the pumps that are also shaking the system, the nitrogen, which is boiling. So, bubbles can hit the inner cryostat and shake it. But, it's easily understandable, and it's a problem that is quite easy to solve. Another feature that is going to be the most important feature of the system is that, as you can see, there are some frequencies that are, for a certain azimuthal number, you have populated frequency above and a certain number, but no frequencies below. And this is actually very important, and I will show you why. Yes. So I just told you that I'm fixing the radius and I'm showing a spectrum, but if you change the radius, the spectrum is also changing because we also have this dependence in our data set, which is radius, time, and angle. So it's interesting because if you go to low radii, the minimum frequency below which nothing, there is no mode population, is higher for small radii and is lower for big radii. So why? We need a theory for that. We need to find a model and try to see if you can figure out what is going on. And yeah, there is a theory was developed by Sam and Patrick and Silke in 2020, and I don't want to spend a lot of time on this because I want to jump to the results, but I just want to say that we have these two parameters, VR and V theta, which are the two velocities of our surface flow. We have a wave equation. We have a field equation for our system. We have a dispersion relation which is modified by the velocity flow, and we want to figure out what is the minimum frequency that can propagate at a fixed radius at a fixed M mode. And you find it looking at turning points and looking at the minimum frequency of all the turning points you have. So we have we have a lot of free parameters and some other like surface tension, density, and height that are determined by experiment, but we have a lot of free parameters. But what we want to do is we want to see what's the velocity profile of our system, because in the end we want to do analog gravity, so we want to see if it's a potential flow, so we want to see the radial behavior of the velocity, of both velocities, angular and radial. So for every radius, for every M mode, we can calculate the minimum frequency for a different velocity values and find the best match with the experiment. And doing this gives you a very nice prediction of the minimum propagating frequency, and moreover, we also get the velocity profile because we can do it for different radii, and for every radius you get a V theta and VR. And if you plot it as function of the radius, you find out that the radial velocity is practically zero, and Silke mentioned before that there is this Ekman, okay, I only have 3 minutes, 5, better. We have radial velocity is practically zero, so we just focus on the angular velocity, and it's a potential velocity. And moreover, having the potential velocity, you can calculate the number of quanta in your system to have this potential velocity, and it scales with the propeller speed linearly. And we also have a big number of quanta of circulation, so big that it's almost a classical vortex flow. So yeah, this is the main part of my talk. And this minimum frequency acts as an effective potential in our system, which means why don't we have frequencies below this minimum frequency? Because if you have a mode with a frequency which is smaller of the minimum frequency, the mode is evanescent, so it's not a propagating mode. And you can see it if you plot frequency against radius. You can see we have bound states, and bound states are these stripes that live between the outer edge of our system, which is just the glass, and the velocity potential, after which the mode becomes evanescent. And if you zoom in and take a slice of some frequency, you can see the absolute value, and you can see that this is looks really like a bound state. Not only this, you can do it for all of them, and you can plot them here and match them with the theory. The theory, I'm not going into the detail, but basically you just take the potential flow the potential barrier, you take the outer edge, and you fit the bound set that can fit in this region. And if you do it for different frequencies, you find the perfect match with the theory. And this is for co-rotating modes for a specific M mode. And also another thing for this, for example, if you zoom in here and you look at this mode, you can literally see where the bound state is hitting the potential barrier and is becoming exponentially decaying, because it's not a propagating mode anymore after this red point in the radial direction, and so it's decaying. This is why below the minimum frequency you don't have any population, while above you do. And yeah, so bound state for co-rotating modes, and yeah, these two plots refer to solid core and hollow core. In the co-rotating, there is not much different. But if you go to counter-rotating modes, so modes that are rotating in the opposite direction with respect to the flow, you see that solid core and hollow core have drastically different features. So in the solid core, you still have a big potential barrier, but it has a peak now. But the peak is very high and is outside the field of view that we can probe. And so you still have bound states, while in the hollow core, we can see the peak in a region where we still have a high resolution. And what you notice is that you don't have bound states anymore above this potential as expected. And you have a big signal, which is zoomed in panel C, which is right on top of our experimental potential. And this is a signature of what we call ring down modes, which are the first aim of the project. And so, yeah, of course, this is only a signature. We don't have anything more than this, but it's already remarkable. Yeah, outlook, and then I finish. So what can we do to improve our experiment? Now that we have a working experiment, what can we do more than what we already did? Well, of course, getting rid of the mechanical noise will be nice. It's always nice to get rid of noise. And well, of course, someone will say, why do you have zero drain? It would be nice to have a non-zero velocity field in the radial direction, because this is connected to black hole horizon and Hawking radiation, which is also a very interesting effect. Detection of light ring modes. So yeah, of course, we have a signature of the ring down modes, but we need more than this to be sure that we are detecting them. Understanding the source of the bound states. So you have bound states. What is creating these bound states? Is it the shaking of the cryostat or something else? Also, nonlinear theory for the amplitude and growth and decay. So if you can measure the onset of these modes and the decay of these modes. So for example, start the propeller and start recording before starting the propeller, so you see the growth of the modes, or switch off the propeller and look how they decay. And yeah, the last thing is, of course, push it to the quantum regime, where you go down from big values of circulation to small values of circulation, so you can actually see the quantization effect, which we don't see right now. Detect individual quantized vortices, which is below our resolution right now, but Vitor will talk about a new detection scheme that we want to apply to be 1,000 times more precise, hopefully. Yeah, noise-free environment is the dream. Yeah, ultra-precise surface reconstruction. Vitor will talk about it. Thank you very much.
Very much, Pietro. Are there any questions, Cameron? So, early on in the talk, you showed some graphs of the minimum propagating frequency and also the increasing M speeds. So, as the radius increases, this dispersion curve is opening up. Is there a radius at which it becomes horizontal unless it's independent of the azimuth? Or it completely.
I think the dependence of from the radius in this plot comes from this equation. So if you change the radius and you look at turning points, you get them for lower frequencies because the radius is larger.
Okay, and then this R to infinity and goes.
Are there any other questions? Patrick?
Maybe I have more, again, like a small comment rather than a question. I just want to point out that, this system that we, developed within the QCMFP program, right? We only had 2 years to actually start basically from scratch. We got an empty lab at the beginning. And within these 2 years, we finally managed to, build a setup where we can actually control this jagged vortex in superfluid helium. And we set up a rather simple, but yet, good enough detection method where we can already see this rather intricate wave-vortex interaction. And thanks to the modeling support by our colleagues in KCL and Newcastle, we were able actually to match our experimental data already with some predictions of QFT on curved spacetimes. Notably, this occurrence of bound states, it is actually something that no one has ever observed before. And the significance is underlined by the fact that actually the inner boundary is not created by a fixed obstacle, it is created actually by the curved spacetime, right? Because the curved spacetime is creating some effective scattering potential, and we can directly probe the scattering potentials, right? So as a future output of this, we have actually lots of work to do, but I think there are actually quite a lot of, hopefully pleasant surprises that are awaiting us along this journey, because as Silke said, this program was established in order to actually have this, theory experimental interaction where hopefully experiments will be able to actually provide some input for the theory. And I'm actually fairly optimistic about the fact that actually we are near that rather thin boundary, where finally experimentalists like me or Silke and Pietro and Leonardo will start actually feeding some inputs to other theorists working also within the ISRQI.
Sounds great. So you mentioned that you can't see the horizon; it's not in your field of view.
The black hole horizon is outside because, well, I said we have a 0 radial velocity from our reconstructions, and I'm saying 0 radial velocity on the surface. Doesn't mean that it's 0 everywhere, because it's draining, but it's not draining in the surface, it's draining in the bulk. It's a 3D system and we just look at the surface. So as Silke was mentioning before, these kind of flows are called Ekman layers, and you have different heights have different flows. And with this technique, we only probe the surface.
So with the current setup, would you be able to investigate Hawking effect?
Well, with this data set, I don't think you can probe Hawking radiation, but maybe something related to the ergo region, superradiance instability, these kind of things, because to probe this, you don't need to see the ergosphere. You can see the effects outside. I don't know, Hawking radiation, probably you need the horizon.
Okay. Are there any online questions, Cameron? Okay, if not, then we can thank Pietro again.
Thank you.
Let's see. Okay. Okay, and for our final talk today, I'd like to welcome Vitor Barroso, who will be speaking about multiplex digital holography for fluid surface profilometry.
How do I put this? 1 second. No, didn't get it in. There we go. Is it working?
No, no, it's not.
Oh, this is.
Yes.
Yes, it's rubbing against my neck. Very comfortable. Okay. Hi, everyone. I'll start thanking the organizers for this really nice workshop. It's really a pleasure to close it. And well, I hope at this point you're already more familiar with what we do in Nottingham in terms of experiments, not only in theory, right? I'll walk you through this new method that we're developing, and I'll try to place it under the umbrella of experiments and also theoretical work that's going around, starting really with why would I need this new method called multiplexed digital holography that was in the title, right? So we heard extensively of the use, the importance, and how good analog gravity can be to raise questions about fundamental physics. Silke brought that up, and several other talks approached that from a theoretical point of view, I would say. But also Leonardo and Pietro showed some very nice experimental results showing this new direction that Nottingham's taking, right? But then it's quite clear for us that, or I hope at least it's quite clear, that to really study these analog simulators in classical or quantum fluids, we have to very well reconstruct these effective field theories, right, that we talk so much about. In our case, this effective field theory resides on the interface of the fluid. So what's important for us is to reconstruct that interface, right? So I put here some of the methods we already use in the lab. So one is the N-shape, which is patent pending that Silke developed several years ago, where you have to put a fluorescent dye in the fluid, so contaminate the sample, and then you can reconstruct waves here in the order of millimeters or centimeters, down to a resolution about of 1 millimeter. But you also have Fourier transform demodulation that Leonardo introduced, where you put a pattern behind your sample. This is the case of the two-fluid sample that Sean and Silvia discussed earlier today, where you can get the resolution of the interface. They also use this in the helium experiment. In this case, you can measure waves around 1 millimeter to 1 micron. So you have quite a large range, about 3 orders of magnitude. But then the question remains, as brought by Pietro, what happens when we make things smaller, right? Or we want to probe even further these effective field theories. So for example, study these ripples or surface waves in thin films of helium, or even just in the large sample of helium we already have. Maybe we want to understand better what's the initial state of that effective field theory. So we need to learn about the noise on that interface before doing the experiment. Or in our case, it was really a choice of downsizing the experimental setup. We can't keep building bathtubs of 3 by 1.5, right? So it made sense to now develop new setups that are more current to our purposes. And in particular, the helium was a great example of it. Now, of course, from the methods I presented, there are some practical limitations. So you have sample contamination, which I would say should be avoided if you can. Our resolution so far is in the order of microns, as Pietro and Leonardo presented, but also Silvia and Sean. You might need multiple separate components. What I mean by that, you need a pattern under the sample, you need appropriate lighting, you need a good resolution camera. So there's a lot to consider to then use the current methods we have, or in the case of N-shape, you actually need a potentially quite expensive sensor sitting on top of your bathtub, right? And a lot of these methods are highly sensitive to refractive index, and in no way I'll claim the method we're developing now, it's not, but it's a concern we always must have. And that's the way I would like to introduce you to digital holography, in this case, through microscopy. So it is a quite extensive field. Rade has also used it for very different purposes. And one of the most important applications of this method is microscopy. So in this case here, you can monitor, for example, the live evolution of cells in a sample. Now, what's this method we're developing called multiplexed digital holography? It's based on everything we learned from what we do in Nottingham through fluid profilometry. So you hear me talking about fluid profilometry. That's the umbrella term for anything that measures the surface of a fluid. So for example, the Fourier transform, the fast checkerboard demodulation that Leonardo mentioned, or Silke's N-shape sensor. But now we merge this with digital holography and a very simple microsome setup. So I'm sure most of you have seen one of these, but instead of having just two mirrors and one of them maybe with a piezo moving around, we just put a sample of fluid there in that basin. And you have a clear relation here between the phase of your interfered beam. So you send a beam through a beam expander. So this will have around 1 millimeter in diameter, come out to whatever size you want. And you send that through a beam splitter, you create a reference. The reference reflects back and goes through the camera. But then this bottom part here, which we call the sample beam, will probe the fluid, reflect from the mirror, and come back and recombine in the camera. This will form interference, as you probably know. And the phase of that interference pattern relates to the path length and the refractive index of the medium you're going through. Now, when you put a sample under this microsome interferometer or in the arm of a microsome interferometer, you can create this cavity effect or this multiple path, where at the reference you have this simple reflection, which is what you would normally use in microsome interferometry. But once you put a fluid, you get this new family of rays. So for example, you have a ray that reflects from the surface of your liquid. You also have rays that go through the liquid and then reflect from the bottom and leave, or do multiple reflections, eventually reaching the camera, right? These are the B rays that I call. Once you do that, you can work out some pretty nasty maths, but very straightforward, to be fair, where you can show that the interference created by the reference in all of these multiple reflections, they decouple into these different phases. And the image you would obtain is something like this. And if you zoom in, it actually looks pretty similar to what Leonardo showed you earlier, so a pattern. So instead of now putting a pattern underneath my sample, I'm generating it through interferometry. And you can model that using image processing, so looks pretty much like a sum of plane waves going in various directions. The direction of that wave is determined by this vector here. And this vector we related by doing the modeling to the tilt of the mirrors, right? So if you have your reference beam and your sample mirror, as you tilt them, you modify this wave number here. So you modify the frequency of these stripes. And once you do the Fourier transform, as Leonardo did, so he explained essentially the entire reconstruction, the digital part. So I will skip there. You get that this interference decouples into peaks. That's a very nice part about this, right? In the FCD method, where you have the checkerboard, you only have two signals, one in this direction and one in this. With our multiplex digital holography, you can generate several simultaneous signals of the same sample, right? Coming from these multiple reflections. And this is, for example, one of the simulations we did using ray tracing. So you essentially just propagate several light rays and try to form a beam and pretend you have a virtual camera there. And you should obtain something like this. And you see that the different families that I mentioned before, so reference and surface of the water, reference and bottom mirror, they really decouple in Fourier space, right? And this is the decoupling we use to then reconstruct those phases that are somewhat related to whatever is in the path, right? But then if I put the sample there, as the light goes through the sample, it acquires the information of the depth of it, right? And that's what we use then to reconstruct really the change in depth. So what you see here is for each of those families, you have different phases. over an entire region of the sample, about 15 millimeters. And I sliced them and turned them into height information, which is this. And that's done through this phase to height correspondence that is written down here. Now, what's so important about this is that each of the family of rays, so RF, FB1, RBJs, they have different prefactors, right? This means that if I have a tiny fluctuation, say fractions of the wavelength, the phases acquired by each family will vary according to the refractive index that the beam went through, right? And what's so nice about this is we learned that they carry different biases as well. So you can think that the ray that went through the reference came back and then went through the fluid and came back. It integrated over all the air fluctuations of the reference and all the air fluctuations of the sample arm. However, if you think of the interference of the bottom mirror and the surface reflection, it actually is completely ignorant of whatever's happening in the reference. And that gives us a very nice way of treating the data and getting really simultaneous reconstructions of the same sample with only one image. And that's really the main message of digital holography. How much can you extract without adding much to your system from one single image, right? So from one single image, I can extract at least 4 simultaneous reconstructions of my fluid. And so I'll walk you through some of the results of a paper that we recently put out. Fairly technical, definitely focused to the optics community, but really the idea is I'll finish with an overview of where we're going with this, right? So first test we did is, well, just put water underneath and see what you can measure, right? So this is the outcome. So we did get interference, nothing surprise here. So you have the stripy pattern that I mentioned we should have. When you do the Fourier analysis of this, in fact, we identified that you have those theoretically predicted peaks that I labeled again. Oh, this died. That I labeled again here. This is also dying. Fantastic. So from each of those families, I reconstructed the height. So we managed to then get height changes in the order of nanometers, as you can see here. And here's where the bias I mentioned becomes very important. So you can see that each family reconstructs pretty well the same qualitative interface, right? So you can see a trend, you can see ripples going around your sample, but some are much noisier than the other, right? And that's something you cannot achieve, for example, with the methods that we currently have. You only have one information, which is the pattern sitting at the bottom or the N shape projecting on the interface, whereas here we have these 4 simultaneous measurements of the same interface, right? And here we can see our gain in resolution. So as I mentioned before, we were in the order of microns, and with these results, we showed that we can go down to nanometers. And that starts maybe giving us hopes of identifying those singly quantized vortices that the helium people are very excited about. This slide really finishes with the time evolution. So this delta t here is the difference between time frames in your camera. So again, only limited by the equipment you're using, so the camera. So you can use a very fast camera or a very slow. It doesn't really matter for the method. This is pretty much what you would get out of one of the reconstructions. So I chose RB1, which is a reference in the bottom mirror. And this is a video of the surface of water when it's being driven by a small piezo from the side. So there's a decent break of symmetry. It's a square container, so you can see a very faint standing wave pattern in one direction. Very hard to see, but it's there. I'll tell you, just trust me. But really you can say, well, is this enough? We went a bit further to really test how precise and if it's really measuring anything. One of the first tests we did is to introduce a known changing volume to our sample, right? So we have a square basin, we put a syringe in, we connected the syringe to a Lego driver, very sophisticated, and we slowly filled in the sample and slowly removed water from it. The black curve you see here is the one that we obtained from tracking the syringe volume. And up here, we used several phases that you obtain from the Fourier spectrum. So I showed you before only 4 of them, but in fact, when you do the analysis, you see that several of them appears for various reasons, Fourier harmonics, digital processing errors, or really just those high order reflections that I mentioned. And you can use all that information to then recover the phases as they change over time. You can see some of them are very noisy, this green curve here. Some are pretty much lie on top of each other. And by statistically treating them, meaning if our assumption that they all measure the same interface is correct, there should be just one set of coefficients, so set of numbers that multiplies each of these curves that will collapse them to 1, right? So I have the green curve, you have this bunch here and this bunch here. If they're measuring the same interface, and it pretty much looks like, right, the same trend, you should be able to collapse them. That's a method known as principal component analysis, very well known. But we were the first ones to implement them and merge with digital holography. And what you get is this averaged blue curve here. I must say this average blue curve includes the 1 standard deviation uncertainty, meaning if you do this for all these 20 curves, I think, 18 at least, you can actually collapse them to 1, take the standard deviation, and that's pretty much what you get. This, of course, does not account for other systematical errors, but is really a display that you are measuring what you're putting in. And our final measurement, I hope, and I'll finish soon, is the liquid evaporation, right? So we just monitor the interface of water and isopropanol over 15 minutes. You can do it for longer as well. And again, using the same analysis, so you have several peaks, you go there, select them, extract various phases, do this statistical method we developed. You get pretty much a good trend in all of them. Again, some of them are noisier than others. Depends, we learned with these experiments that it depends also on the sample. So we have to see how it goes on the helium. And we managed to find very decent evaporation rates. We don't have theory for evaporation rates. It was not our purpose here. Again, this is an optics paper, but pretty much in agreement with what we could find in the literature, okay, within reasonable range. Now, to conclude, I hope I convinced you you can actually measure things using this method. But why is it so good as a recap, right? Well, we're now down to the order of nanometers resolutions. So we did gain almost 3 orders of magnitude in our setup. It's a very simple setup. It's a microscope interferometer. You can go to any undergrad lab in most universities and you'll find one. But our purpose here was to keep it simple in the optics and spend a lot of time in the processing, right? And that's why we applied for a patent for this processing pipeline that we created. And we're currently trying to find industrial applications within the network grant of QCMFP and QTFP. Silke mentioned that already. But I think from the scientific side, with all of you are mostly interested in, we want to now see if it works in superfluid helium. That's the simple answer here, right? We want to see if we can reproduce what we already know, for example, from the experiments that Leonardo and Pietro discussed. Maybe we'll resolve those singly quantized vortices that Carlo is very excited about. I think there's a lot of new physics coming. Hopefully the back reaction that Adam presented earlier today will be able to identify also by doing this constant monitoring of our interface in an analog experiment for the Unger effect. And I'm pretty sure there's much to be learned from fluid interfaces. And I hope I convince you it's worth investigating a bit more and developing also new methods experimentally. Okay, so that's it. Thank you. Thank you.
At what point of resolution do we start to reach the point where it no longer makes sense to just be viewing a deterministic fluid surface? So we don't expect a quantum field to be something that we could just look at and be able to deterministically reconstruct its entire history.
Yes, it's a very good question. It's actually one of the things we're trying to learn. But my simple answer to that is, so the concept of the interface has a breakdown, right? It's I would say almost obvious. Once you get to a molecular level, as Silke explained, I think the two-fluid experiment is a very simple case where you have the molecules really just swapping right around that level, but without being able to penetrate completely the other fluid. That's what defines the interface. But of course, that has a thickness, right? But at the same level, you could say, well, can I model that by a surface, a two-dimensional surface, right? Of course, embedded between those three-dimensional fluids. And can that surface fluctuate less, well, to a scale smaller than the molecules itself? It can. Well, I don't know if it can collect it. That was not the question, right? Yeah, we'll not go that far. Yeah. Well, okay. Well, that's a different question. I would not go that far. Okay. The classical interface is not quantum. I mean, not to the levels we're talking about here. All I can tell you is I do think you can model the interface as this two-dimensional mathematical object where you can play around and use the Navier-Stokes equations, and beautiful things happen. And that can fluctuate to scales much smaller than its actual thickness, right? But there is a point where everything breaks down, and then you have to take into account this molecular motion, right?
So do you think that happened before, for instance, I would see some sort of...
I think so, yeah. Yeah, in a classical fluid, yeah. I would say very much so, because you can think that the thermal component, the KBT, right, is extremely larger than your h bar omega, if that makes sense. Yeah?
Patrick? Yeah, actually, I would like to more other little comment. Actually, in connection to what was discussed about these length scales, right? So Vitor has shown us that he has a resolution down to nanometers, right? The atomic scale, I mean, the actual size of a helium atom is somewhere, around 1 angstrom, so over 1 nanometer, which is only 1 order of magnitude apart, right? And me as an experimentalist, I'm so excited to see actually if this method works in superfluid helium. We will be probably the first ones to see actually the macroscopic, profile of a quantum vortex terminating on a free helium interface. The prediction is that actually this quantum vortex will create a rather shallow depression, about 50 nanometers in depth, and about 100 microns in diameter, right? Which what I'm seeing here is actually well within the reach.
I believe so.
Right?
Yeah.
And the only issue is really just to get very good control about all sources of noise.
Yeah, exactly. Yeah.
Which is what we are actually quite quickly going towards.
Yeah, I think so. I mean, I think this is one of the most exciting things about. Of course, I'm very interested in the industrial part. Of course, we were yesterday presenting this to try and find industrial partners, but from the scientific side, it's probably the most promising direction we want to take. Yeah.
Actually, one thing that I would like to mention is that if you take solid-state physics, you have very advanced scanning electron microscopes.
Oh yeah. Which much higher resolution. Yeah.
Decades, and the equipment costs millions, right? Here, we are powering this almost with a laser pointer.
Yeah, exactly. So I mean, I think that keeps being the message of what we're doing, right? We try to keep it simple and cheap. It's likely for the helium we'll have to crank it up in many ways, but in any case, the idea behind the method is still there, right? And interferometry works, it continues working. I think it should work there as well.
So you mentioned that when you had these more simultaneous measurements of the surface, some of them have more noise. Is it that they're more sensitive to outside noise, or is it just part of the measurement scheme that some of them will have inherent noise?
Yeah, so both. I'll go back to this beautiful design from August. You can think that, for example, let's take the R beam. When I put path length here, I really mean I'm integrating, right? You can think of a wavefront of the beam as it walks towards the reference mirror and comes back. It's integrating over, it's accumulating the information of where it's been through, right? So if you have, say, an air current here or a temperature gradient, the reference is acquiring that, right? Same here. Now, of course, this gives each of these reflections different, what we call noise bias, right, would be the technical term. But more than that, right, the beam that reflected from the surface twice has an absurdly smaller amplitude than the reference, right? In fact, in water, the F beam will be about 14% of the incident light, and well, this will then continue exponentially down, right? So that's one of our main problems, I would say. So you have this inherent bias, yes, but I would say the main issue we find in the experiment is that, for example, our B2 means that it's reflected twice from the bottom mirror, has such a low intensity that it's very hard to resolve anything out of the interference. And that's why it becomes so noisy. Yeah.
Adam?
So there's an issue with the Schiattarella demodulation technique where you can't look at the hole in the flow conditioner.
Yeah. Mm-hmm.
Could you look at that with this technique, with just the F thing that bounces off?
Well, if there's no hole, right? If there's a hole open, not much we can do. The light will just go through it, right? Yeah, there's only so much you can do. We can't do magic yet. But if it is a dimple, yes, you should be able to. The only problem is once you have a dimple, you can imagine that one of our assumptions, fairly strong one, is that, well, you can see I drew a flat interface here, right? Very important. This flat means it needs to be, at least on average, within the time scale of our experiment, it has to be fairly flat, right? With tiny waves on top. If you have a strong gradient, you can think that the F beam will come and just go away, right? And there's no interference in there. So this is a problem we'll have to test and see if it works. Yeah?
Any other questions? If not, then we can thank Vitor once again.
I'll take this off.
And so that concludes today's conference. Thank you very much for watching online. And thank you very much for people who are here watching in person. You can maybe invite Cisco and Cameron back up to the front. And I'd also like to thank Rick, the puppet master behind the scenes, pulling the strings. Take it away.
Thanks, Leo. Thanks, Cameron. Thanks, Cisco. The organizing this conference was entirely on them. I said, guys, talk to everyone, get them to submit the abstracts. Just make sure it's not too long, and I'll handle the broadcast. Just make sure that this is the date. They followed everything perfectly. They talked to everyone. They got us the coffee break. They made sure that Silke and Jorma would be here. And so, yeah, these guys, please, now thank them. And additionally, I'd like to thank Jorma and Silke for hosting me for this week. And to be honest, all of the group, it's been a pleasure to spend the week here with you guys. So thanks a lot for that. And finally, next week at 12:30 Central European time, we're going to have the RQI Circuit in Vienna. Czeslaw Bruckner, Markus Müller, Markus Aspelmeyer, Marius Christodoulou, lots of PhD students, lots of postdocs, all talking about the very cool research that they do in Vienna. You guys did an excellent job showcasing the work that you do here. And I was very excited to hear about everything like in this concise way and kind of like telling the story. This is very cool. So now Vienna will do the same. So tune in and thank you so much for being here. Thank you so much for watching. And until next Friday.